Good evening, friends. Welcome to day 7 of the Six Sigma Masterclass Elite sessions. So yesterday we were discussing about probability distributions. So discrete data probability distributions, we have binomial distribution and Poisson distribution. So binary discrete data would follow binomial distribution and the primary metric is proportion, and count discrete data would follow Poisson distribution and the primary metric is average. Then we looked at the very famous continuous data probability distribution called normal distribution. But before that, we understood about a very important property of standard normal distribution. So for a standard normal distribution, the mean will always be equal to 0 and the standard deviation will always be equal to 1. Then we looked at the area coverage within various sigma limits for a normal distribution. So within one sigma limit, the area coverage will be 68.27%. Within two sigma limits, it will be 95.45%. And within three sigma limits, it will be 99.73%. And then we also looked at how to calculate the actual sigma level. So if the mean is aligning with the target or if the process is centered process, then use we need to apply either the LSL side formula or the USL side formula to calculate the sigma level. But then if mean is moving away from the target, or if it is tilted towards the USL side, then we will apply the USL side formula to calculate the sigma level. Or if the mean is tilting towards the LSL side, we will apply the LSL side formula to calculate the sigma level. And then we also derive the relationship between the long-term and the short-term sigma level. So the long-term sigma level will always be 1.5 less than the short-term sigma level as per Motorola. So let us continue with our discussions. So we will look at the normality test to begin with. And as part of it, we will also look at how to convert a non-normal distribution into a normal distribution.
Hi, Sridhar. Good
Yeah,
evening.
yes, please.
Sridhar, I have a question in a practical scenario.
Mm,
Just like, if one person is doing a Six Sigma project,
mm.
so I'm working on one where we are working on process improvement and performance improvement.
Okay.
Uh, so if someone is working on a Six Sigma project, or maybe at the level of Six Sigma,
Mm,
what will be the goal here? So goal, what we define as we need to improve, but
mm.
where do we stop? Do we achieve exact Six Sigma, or we just
No, 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 no.
look for
See,
the improvement?
no, it all depends on the baseline scenario, right? So if you're, as we discussed about this quite extensively when we covered the project charter, correct? So how to fix the project goal? So the project goal should be achievable yet aggressive. So you are performing somewhere, say around 80% efficiency mark. You
Hmm.
cannot aim to achieve 99% in one single project exercise, correct?
Yeah,
Then you
yeah,
will
right,
not be able
right.
to close the project forever. So it
Yeah,
should
yeah,
be a
right.
realistic goal. Yeah, it should be a realistic goal. It should be
Exactly,
something
exactly.
that we should be able to achieve, right, within the
Okay,
agreed timeline. And
okay.
at the same time, it should be aggressive. So just because it should be an achievable goal, so you cannot
Hmm.
fix a target which can be
Hmm.
easily achieved. So
Yeah.
as I told you,
So,
if your current performance is 96%, so there is no point in fixing up a target as 96.5%, right? So that can be easily achieved. So it will not
hmm.
be considered as a Six Sigma project. Six Sigma means you are expecting a breakthrough process improvement. So even
Hmm.
though it may not be achieving that Six Sigma level, but
Hmm.
your current Sigma level is somewhere around 2.5. Even
Hmm.
achieving a 3.5 Sigma level will be considered as a very good improvement.
Okay, okay. So it is like, moving performance from, let's say, 50 to 60% towards
Yeah, we need to
85%.
do a phase-wise approach.
Yeah,
So
yeah,
we
yeah.
cannot take a
So
over-aggressive
probably
target.
I will take a guidance from you
Yeah, yeah,
offline
yeah, yeah. So that's what I told you,
to
right?
submit a
So
report like that. Yeah.
yeah, yeah. So the thing is, after the training sessions are over, so
Hmm.
you can start working on a project exercise.
Yeah,
So
yeah,
when you start working on a project exercise, I will definitely, provide you with mentoring assistance if at all you need anything.
yeah, yeah,
So it may not be on a frequent basis, but then at least once in 10 days or whatever, right? We can
yeah,
always
yeah.
connect and then discuss. No
Yeah,
problem.
definitely. The project is kind of now completed, but I
Okay.
wanted to submit a complete documentation for that. And that too, I will, as you said in the start, that we can also submit a report here in IMC and get a certification
Yeah,
there
yeah,
as
yeah.
well.
Yeah,
So
project
I'll check
completion
with
report.
my superiors whether this data can be shared outside or not.
Mm.
Only then we can go with that. But inside the organization, I wish to submit such a report.
Yeah, yeah, that will always really help you, right? So you can always,
Yeah.
correlate with whatever you are learning currently, right? Whether you have
Mm-hmm.
applied all these
Yes,
concepts
yes,
or
yes.
not. So it's
So
not like,
some or the other way I have applied it, but the way that you just shared yesterday
mm,
was a eye opener actually.
okay.
Yeah, yeah,
That's what. So learning new things, implementing new things,
yeah,
that's the goal of this entire
yeah,
session,
yeah.
right? So
So what
if
we
I'm going
learned,
to talk
yeah,
about certain aspects which you already know, then
exactly.
you will not
Mhm.
get that value add, right? So,
Exactly. So whatever path I took, since I was not aware of these tools and
mm, mm,
methodologies, I took a
mm,
long way, but achieved the
mm.
goal. But
Okay.
I can, while submitting the report, I can probably
Sure, sure.
mention that was the
Yeah,
path I
yeah.
have taken.
Yeah. Definitely.
Yeah.
So I
Thank you,
will
Sridhar. Yeah.
definitely, if at all your organization allows you to share the project document to an external source, I
Mhm.
can definitely look at it and then I will come back with my comments, so that you
Sure,
can
sure.
refine the project document and then make it a full-fledged Six Sigma project document.
Yeah.
And we can also look at submitting it to IMC for obtaining the project completion certificate.
Yeah, sure,
Okay. Okay.
sure.
Yeah. So let me share my screen. And as I told you, you'll get started with the normality test. So let me put today's date, which is 15th of Jan. Right. So just to validate, whether a continuous data set follows normal distribution or not. So we need to perform this normality test in Minitab, right? So this is yet another instance wherein we'll be completely dependent on Minitab to provide us with the final result. So the earlier one that we actually saw, wherein we were completely dependent on Minitab, was the continuous data measurement system analysis, wherein we at least were able to perform some preliminary analysis, right, and then infer that the repeatability variation is significantly higher than the reproducibility variation. But then for the exact numbers, we had to be dependent on the Minitab to provide us with the result. This is yet another case. So these are the two instances where we'll be completely dependent on Minitab to provide us with the result. Otherwise, all the other statistical analysis we'll be able to uh, do both in Excel as well as in Minitab, right? So you can also get oriented on how to perform all those analysis in Excel. But then for most of the statistical tools, as I told you, I've also given the template so that you can learn how to navigate the template, right? But then if I'm going to show only, solving all these problems using the template, then it will appear like a magic to all of you, right? So you'll not be able to really appreciate the calculation logic behind all these calculations. So it's better that, I explain to you the calculation logic so that you can also kind of understand the formula that was used. But then if you find it difficult to understand the calculation logic, as I told you, so you can always, use the template wherein you can simply input the values and get the result. But in the assessment, always, use the template so that you can save lots of time. So the normality test, the name of the test is Anderson-Darling test. So this is the one which we are going to perform in Minitab in order to validate the normality of a data set. And when it comes to Minitab, obviously you'll be referring to this metric called p-value, right? So p-value is the metric which we referred. when we wanted to validate the randomness in a data distribution. So when we construct the run chart and we wanted to validate the randomness in a data distribution, we use the p-value, right? So of course there were four rules which we could apply visually and then find out if the data distribution is non-random due to any of the four non-random characteristic. But then as I told you, Minitab, if you are going to use Minitab to construct the run chart, so Minitab will also provide you with the p-value. So the p-value is a metric with which we will be able to infer whether the data distribution is random or non-random. A similar way, so here again, we'll be using this p-value and then would be validating whether the data distribution is normal or non-normal. So what is the criteria? So the p-value is greater than 0.05. We can infer that the data distribution is normal. Again, the relevance of 0.05 as the criteria value we will definitely discuss as part of the analyze phase. So once you learn about the concept of testing of hypothesis, then you'll be able to appreciate this 0.05 logic much better. So that is why, I have parked it till the discussion of the testing of hypothesis concept, which will be part of the analyze phase. So once we understand about what is confidence level, confidence interval, etc., you will be able to appreciate how come we are considering zero point zero 0.05 as the criteria for p-value, and under what circumstances we need to consider zero point zero 0.05 as the criteria for p-value. So that is very, very important. So here for the time being, just understand that if p-value is greater than 0.05, then we need to infer that the data distribution is normal. On the other hand, if the p-value is less than 0.05, then we need to infer that the data distribution is non-normal. And once we come to know that the data distribution is non-normal, we will also look at how to convert that non-normal distribution into a normal distribution. So why do we need to convert a non-normal data set into a normal data set? Because as I told you yesterday, there are a good number of statistical tools and techniques which can be applied only if the data distribution is normal. Because only if the data distribution is normal, we can even use the statistical metric called mean, right? So the data distribution is non-normal, then we need to use the statistical metric called median, right, as a measure of average. So mean has got quite a good number of statistical tools and techniques which can be applied for necessary analysis. Since we can dig deep and then analyze much better, so people would actually try to convert a non-normal distribution into a normal distribution. So we will also look at, how to convert a non-normal data set into a normal data set by following a stepwise approach. But before that, we will see how to validate whether the data distribution is normal or not. So for that, we'll go to the exercise file and click on the next sheet titled Normality Test. So we have the exercise here. So we have been provided with the processing time in minutes for some 100 sample units. So we have a very good sample size. So for 100 sample units, we have the processing time given in minutes, and we are being asked to validate whether the processing time data distribution is normal or non-normal. In case if it turns out to be non-normal, then how to convert that non-normal processing time data set into a normal data set, right? So two parts to this particular exercise. So the first one, we will validate whether this data distribution is normal or not, right? So since we need to perform this Anderson-Darling test in Minitab, so I will just copy paste the entire table in the Minitab worksheet, right? And we need to go to stat, basic statistics. Under that, we find this normality test. So stat, basic statistics and normality test. Just click on that. So the dialog box will open. So what is the variable for which we are validating the normality? So it's the processing time data set. So double click on that column header so that it appears inside this variables field. and then we will click OK. So Anderson-Darling test would have been chosen as the default test for normality. So no need to change this. And we can straight away click OK here. So you'll get to see the probability plot. But then you can straight away look at the p-value that is displayed in this box here. So p-value, as I told you, if it is going to be greater than 0.05, then we can infer that the data distribution is normal. But if it is going to be less than 0.05, we need to infer that the data distribution is non-normal. But here, the p-value shows less than 0.005. It's not even less than 0.05, it's less than 0.005. So this data distribution is pretty much non-normal, right? So p-value is so low, it is even less than 0.005. Even if it is less than 0.05, we need to infer that the data distribution is non-normal. But here we find the p-value to be less than 0.005. So that means this data distribution is pretty much non-normal, right? It is robustly non-normal. So that is what we can say. So converting this into a normal distribution, it will be a challenging exercise, but we'll also look at how to do that. But before that, let me just copy paste this graph in the exercise sheet and then provide the inference. So ideally, if the data distribution happens to be normal, the p-value will not only be greater than 0.05, but we'll also find all these data points, right? Most of the data points falling right on the slope. So you can find a slope here. So this is the probability plot graph. So at present, you don't find too many data points pertaining to processing time falling on this slope. In fact, it is forming a curve around the slope. So that's why we have the p-value as less than 0.005. So ideally, the data distribution is normal. You would find most of the data points falling right on the slope. In that case, the p-value also will be greater than 0.05. So for this, let us provide the inference. So the inference will be, since the p-value is less than 0.05, we can infer that the processing time data distribution is non-normal, right? Now, if it is non-normal, then how to convert this into a normal data set? As I told you, we have limited set of statistical tools and techniques that can be applied for a non-normal distribution. So the tendency would be to convert the non-normal data set into a normal data set. But the only risk here is we need to be prepared to lose some critical information about the original data characteristic. So when we convert a data set into a normal data set, a non-normal data set into a normal data set, so there will be some loss of information with regard to the original characteristic of that data set, right? So whatever processing time data set that we have, so when we convert this into a normal data set, we should be prepared to lose some of the critical information regarding the characteristic of this processing time data set, right? So that is the only challenge. So if you are prepared to kind of forego some loss of information or some critical information with regard to the original data characteristic, then we can always proceed with that conversion exercise. But then if you ask me, I'm not a big fan of converting a non-normal distribution into a normal distribution. I would prefer having the data distribution as it is, even though we have limited set of statistical tools that can be applied for the metric called median. But still, I would like to go ahead so that, we don't lose any critical information about the original data characteristic. So that is why, we even follow a stepwise approach. So if you are able to convert the non-normal data set into a normal data set immediately after the first step, then there will be limited loss of information about the original data characteristic. But then if you are able to convert a non-normal data set into a normal data set after the final step, right? then there could be a severe loss of information about the original data characteristic, which we need to accept, right? So let us look at the stepwise approach that we are supposed to follow in order to convert a non-normal data set into a normal data set. So the first step is to obtain the square root values for the processing time data set, which has proved to be non-normal. So once we have the square root values for each and every data point pertaining to the processing time, then we would validate the square root values data set for normality. So if it passes the normality test, then we can stop then and there, which would mean that we have successfully converted the processing time non-normal data distribution into a normal distribution by obtaining the square root values, wherein the loss of information about the original data characteristic will be very, very minimal. So if you are able to convert immediately after the first step, that is, if you are uh, probably having a scenario wherein the square root values data set passes the normality test, then you can feel happy that the loss of information about the original data characteristic will be very, very minimal. But then if the square root values data set fails in the normality test, so you will test for normality and you find the p-value still less than 0.05, even for the square root values data set, then we need to proceed to the next step. So what is the next step? So we need to obtain the natural logarithmic values for the original data set pertaining to the processing time. So once we have the natural logarithmic values for each and every data point pertaining to the processing time, we would validate the natural logarithmic values data set for normality. So if we are able to successfully convert the non-normal processing time data distribution into a normal distribution by obtaining the natural logarithmic values, you can stop then and there. But if the natural logarithmic values data set also fails in the normality test, then as a final step, we need to perform a transformation called Box-Cox transformation. So this Box-Cox transformation is a very, very robust transformation, right? So even if the non-normal distribution is very, very rigid and robust, this Box-Cox transformation can actually convert those rigid non-normal distributions into normal distribution. But then when we actually resort to this Box-Cox transformation, we should be prepared to lose some critical information about the original data characteristic, because the loss of information when we actually perform that final step is going to be very, very severe. So if we are able to successfully convert the non-normal data set into a normal data set immediately after the first step, the loss of information about the original data characteristic will be minimal. But if you are able to convert only after performing the Box-Cox transformation, the loss of information with regard to the original data characteristic will be very, very severe, right? So that's the take that we need to kind of decide, right? So whether we would want to have the original data characteristic retained as it is, and then deal with the limited statistical tools and techniques that can be applied for a non-normal distribution, or we are prepared to lose some critical information about the original data characteristic and still go ahead, converting that non-normal data set into a normal data set. So let us look at the stepwise approach. So what we am going to do, so as the first step, so I'm going to obtain the square root values for each and every data point pertaining to the processing time. So how to get the square root value for a data point in Excel? We need to apply the formula is equal to SQRT and then provide the reference of the original data point. That's it. So you'll get the square root value for the original data point. So this formula can be copied for all the other 99 data points. Right? And now let me validate the square root values data set for normality. So I'm just going to copy paste the square root values data set column alone in Minitab worksheet. Close this. Right. So paste as a single column. And now let me test this for normality. So I need to go to stat, then basic statistics, normality test, and I will give the reference as square root values of the processing time, and then click OK. So as we can see, it's much better than the earlier scenario. So when we actually perform the normality test for the original processing time data set, it was far more worse than this, right? But here at least we could see the p-value, right, showing an encouraging sign in the sense the earlier scenario it was less than 0.005. Now we find the p-value to be 0.011. It's still less than 0.05. So we can say that the square root values data set has failed in the normality test. But the encouraging sign here is the non-normal data set is slowly getting converted into a normal data set. So when we obtain the square root values, we can find a much better p-value than what it was when we actually validated the original processing time data set for normality. And as we can see, the data points, the square root values, data set, the data points, they're also pretty much falling all along the slope, right? So we can see most of the data points falling on the slope, and the p-value is also getting much better. So the data conversion is definitely happening, but as far as the square root values data set is concerned, it has failed in the normality test because we still find the p-value to be less than 0.05. So that's the inference we are going to come up with. Let me just copy paste this graph, the exercise sheet, and then provide the inference. So what will be my inference? So the inference will be, since the p-value is still less than 0.05 for the square root values data set, we can infer that the square root values of the processing time has failed in the normality test. So still the data is non-normal, right? So what is the next step that we need to perform? So we need to now obtain the natural logarithmic values for the original data set pertaining to the processing time. So the natural logarithmic values for each and every data point pertaining to the processing time is what I'm going to calculate now. Again, I'm going to apply the Excel formula to obtain the natural logarithmic values. So the formula is very simple, is equal to ln. So put is equal to ln and provide the reference of the original data point. That's it. You will get the natural logarithmic value for a particular data point. Now the same formula can be copy pasted for all the other 99 data points. Right? And then let me just copy paste this natural logarithmic values data set in the Minitab worksheet and then test this for normality. So go to Minitab and let me paste this in the next column. Paste this as a single column. Right. And then let me test this for normality, stat basic statistics, and then normality test. So we need to provide the reference as natural logarithmic values of the processing time, and we click OK. Now we find the p-value to be greater than 0.05, right? The p-value has become 0.439, right? Even when we, validated the square root values data set for normality, we could observe that the p-value was becoming much better, right? So we could understand that the conversion is definitely happening at the back end. But then since the p-value for the square root values data set was still less than 0.05, we inferred that the square root values of the processing time has failed in the normality test. But then when we obtain the natural logarithmic values for the processing time data set, we could find the natural logarithmic values data set passing the normality test, right? So we find most of the data points pertaining to the natural logarithmic values data set falling on the slope, and the p-value has also crossed that 0.05 criteria. So it is in fact 0.439. So p-value greater than 0.05, we need to infer that the data distribution is normal, right? So we don't have to really perform the third step, which is the Box-Cox transformation. So we can stop with this because we have been able to successfully convert the non-normal processing time data set into a normal data set by obtaining the natural logarithmic values. So the inference will be, since the p-value is greater than 0.05, we can infer for the natural logarithmic values data set. So we can infer that the natural logarithmic values of the processing time has passed the normality test. And there is absolutely no need for us to perform the third step, which is the Box-Cox transformation, because we have been able to successfully convert the processing time non-normal data set into a normal data set after the second step itself, right? But then still, let us perform the third step. So I will show you how to perform the Box-Cox transformation in Minitab so that you can get some idea as to how to perform this exercise. So wherein the normality will be much more robust than the earlier natural logarithmic values data set, right? So the natural logarithmic values data set, the p-value was 0.439. So just remember this value. But when we perform the Box-Cox transformation, and if you are going to perform the normality test for that Box-Cox transform data set, then we would be able to find the p-value in excess of 0.439 because this is a robust conversion methodology. So for performing the Box-Cox transformation, we need to go to again stat, and then we need to choose control charts. Under control charts, we have this Box-Cox transformation. Just click on that and it will uh, ask you all the observations for a chart are in one column. So that is how we have arranged the data. So we need to provide the processing time data column as the reference, and the subgroup size will be the sample references, right? And we click on options and it will ask you where to store the transform data. So I would want the transform data to be stored in the very next column, that is column C3. So I will provide column C3 as the reference for storing the transform data. And let me click OK at both the places. So you'll get to see a graph, but let us close it. So we already have the transform data displaying under column C3, right? So all the 100 data points have got transformed using the Box-Cox transformation. So let me provide this column header as Box-Cox, right? And let me just validate this for normality. So we again need to go to stat, basic statistics and normality test. And the reference I'm going to provide is Box-Cox, and I click OK. So as we can see, this is much better than the natural logarithmic values data set. The p-value is also like 0.809. For natural logarithmic values, as you would remember, the p-value was only 0.439. Since it was greater than 0.05, we can always infer that the data distribution has become normal. But then if you look at Box-Cox transform data set, it is much more robust, right? So the p-value is definitely much higher than what we saw for the natural logarithmic values data set. And also, if you look at the probability plot, right, we find most of the data points lying right on the slope. So this is also another indication. But as far as this exercise is concerned, as I told you, there is no need for us to perform this Box-Cox transformation. Just to demonstrate, how to perform this Box-Cox transformation, and also the fact that Box-Cox is a very robust transformation methodology. And obviously, the p-value for the Box-Cox transform data would be much higher than the natural logarithmic values p-value. right? But then the only catch here is we need to be prepared to forego some critical information about the original processing time data distribution characteristic. So this is how we would validate whether a data distribution is normal or not. So in case the data distribution is non-normal, then the steps to be followed to convert a non-normal data set into a normal data set. So this is what I have summarized here. So the first step would be to obtain the square root values for the original non-normal data set and validate the square root values data set for normality. If the square root values data set fails in the normality test, then what we need to do? We need to obtain the natural logarithmic values for the original data set, and we will validate whether the natural logarithmic values of the original data set passes the normality test or not, right? If the natural logarithmic values also fails in the normality test, then as a final step, we will perform this Box-Cox transformation, right? So for those who may ask this question, why can't we actually perform the Box-Cox transformation straight away? Because if that is going to be a robust conversion methodology, so why to follow this stepwise approach? Because we need to remember that when we perform the conversion act, there could be severe loss of information with regard to the original data characteristic. So when we actually kind of find that we are able to successfully convert a non-normal data set into a normal data set, immediately after the first step, the loss of information about the original data characteristic will be very, very minimal. But if you are able to convert a non-normal data set into a normal data set, only after performing this Box-Cox transformation, we can understand that the loss of information with regard to the original data characteristic will be very, very severe, right? So that is why it's advisable to follow this stepwise approach. Fine. So this is about normality test and conversion of non-normal data set into a normal data set. So the final chapter in the measure phase is process
Sorry,
capability.
can I
Yeah,
ask
yeah.
why in the first place we do this normality test?
Because you would want to find out, right, whether you can use the statistical metric called mean. Otherwise, how will you know that the data distribution is normal or non-normal? So only if the data distribution is normal, we can use the statistical metric called mean. And we have certain good number of statistical tests which can be applied for mean as a statistical metric. So if the data distribution is non-normal, then we need to use the statistical metric called median. And we have limited number of statistical tools which can be applied for median. I thought I explained this very clearly at the beginning, right?
Yeah, maybe I
So
missed it.
continuous data, you need to definitely, perform this normality test and find out whether the data distribution is normal or not. Then only we'll be able to use mean as a statistical metric, right? But then if you find outliers present in the data set, so you construct a box Whisker plot and you identify the outliers that are present in the data set, straight away we can infer that the data distribution is non-normal, right? So you don't have to really even don't even need to perform the normality test to prove that point. So straight away we can infer that the data distribution is non-normal and we cannot use mean as a statistical metric for that scenario. But then if you're not able to find outliers in the data set, but then you want to test for normality, you can perform this normality test and find out. Right. So the final chapter in the measure phase, as I told you, is process capability analysis. So what is process capability? So process capability is the ability of the process to meet the customer requirements. So when we perform this process capability analysis as part of the measure phase or towards the end of the measure phase, so we are trying to derive the baseline process capability of the process, right? So we are trying to derive the baseline process capability of the process. So we would be actually expressing the CTQ metric in terms of sigma level when we perform this process capability analysis. So yesterday itself we saw how to calculate the sigma level for a continuous data distribution, which is normal, right? But then when we actually uh, learn about the process capability matrices, the sigma level also will be part of it, right? The sigma level calculation also will be part of it. But then we haven't yet seen how to calculate the sigma level for a discrete scenario. So whatever, sigma level calculation that we saw yesterday was for continuous data, which is normal. But we are yet to see how to calculate the sigma level for a discrete scenario, which we are going to see in a short while. And also for the continuous data, right? So when we calculate the process capability matrices, so we are going to look at what are all the, process capability indices that we have for continuous data. And from that process capability indices, how to convert or how to arrive at the final sigma level. So the sigma level that we would calculate for the continuous data process capability analysis is not different from the sigma level that we saw yesterday. So whatever formula that we used yesterday is a conventional formula for calculating the sigma level for a continuous data distribution, which is normal, right? But what we are going to see today as part of the continuous process capability analysis, the sigma level calculation can also be done through a different method. That is, we'll be using one of the metric to calculate the continuous process capability, and we are going to calculate the sigma level from that metric as well. So this is another route that we are going to see, right, with regard to sigma level calculation for a continuous data, which is normal. But apart from that, as I told you, we haven't yet seen how to calculate the sigma level for a discrete data scenario. So that is what we are going to see first. So first we are going to look at the discrete process capability analysis. So let me just go back to the exercise file. So when we talk about the discrete process capability analysis, so I'm going to click on the sheet PC discrete. So before even looking at the exercises under PC discrete, which are very, very important from the assessment point of view. But before that, let us try to find out the difference between a defect and a defective, right? So you might have, seen these two terms being used quite frequently, right? Defect and defective. But what exactly is a defect and what is defective? So many people may think that these two terminologies are pretty much the same, right? But we need to understand that these two are different terminologies. They are not same. They cannot be used interchangeably. So these two are different terminologies. So we will first understand the difference between a defect and a defective through a very simple example. So this is the example of invoice data entry process. So let us not get into the nuances of this invoice data entry process. So what we need to understand is the employees are required to fill in these four fields that you find here as the column headers. So the invoice date, the vendor code, the amount, and the goods received date. So these are the four fields which the employees are supposed to fill in as part of the invoice data entry process, right? So an inspection was carried out uh, uh, with regard to these five samples, and we could find the first sample, couple of errors were identified under amount and goods received date. The second sample was absolutely fine, so no error was identified. And the third sample, again, couple of errors were identified, this time under invoice date and the amount. And the fourth sample, again, an error was identified under invoice date, and the fifth sample was absolutely fine, right? So we had errors in the first sample, the third sample, and the fourth sample. The second and the fifth samples, they were absolutely fine, right? So now with regard to count of defects, we will always be looking at the errors committed at an inspection parameter level. So each and every field that the employee would be required to enter is an inspection parameter here, right? When we perform the quality inspection, the quality inspectors will check all these four fields, whether the employees have entered the right value or not. So the errors identified at an inspection parameter level is what we would call as a defect, right? So from that perspective, if you see, sample 1 has got couple of defects, amount and goods received date. Sample 3, couple of defects, invoice date and amount. And sample 4, one defect that is under invoice date, right? So what is the total count of defects? So two defects in
5.
sample 1, two defects in sample 3, one defect in sample 4, so 5 defects. But defective, we need to understand, is always referred from a unit perspective. A sample unit can either be defective or non-defective, right? A sample unit can either be defective or non-defective. So if a sample unit contains one or multiple defects in it, the entire sample unit will be called as a defective sample. So we are not bothered as to how many defects are there in a particular sample unit, but the entire sample unit will be termed as a defective. So even if one defect is identified in a sample unit, we would call that entire unit as a defective unit. So defective is always referred from a unit perspective, right? So unit can either be a defective or a non-defective. So if you uh, consider from that perspective, so sample unit 1 has got couple of defects in it, but entire unit will be termed as a defective unit. Similarly, sample number 3, which has got couple of defects, the entire unit will be called as defective. Sample unit 4, even though we have only one defect in it, but then the entire unit will be termed as defective. So what is the defective count in this particular scenario? Defective count is 3. Sample unit 1, sample unit 3, sample unit 4. So there are 3 defectives, whereas defect count is 5, right? So defect is the error identified at inspection parameter or quality parameter level, whereas defective is always identified at a unit level. A defective unit can contain one or multiple defects in it. So we need to be very, very clear with this distinction between the defects and the defective, right? So 5 is the number of defects in this example, and 3 is the number of defectives in this example. But as a customer, in which particular metric he would be interested, defects or defectives? So as a customer, just think yourself as a customer. Will you be interested to know about the defect count or the defective count?
Defective count, sir.
Defective count, right? Very good. Defective count. Because as a customer, I'm least bothered whether a sample unit contains one or multiple defects in it. The entire unit will be rejected as a defective unit by the customer, right? So you go to a garment shop. So you plan to buy a shirt and you find a small thread hanging out of the pocket. So will you still go ahead and buy that piece? Definitely not. You will reject that piece as a defective one, right? And you will try to buy some other thing. So the same way as a customer, I'm least bothered about how many defects are there in a particular defective sample unit. I would be rejecting the entire sample unit as a defective, even if there is going to be one defect in it, right? So the customers would always be interested in knowing the defective count. But then as a service provider, I would want to perform necessary analysis in order to arrest the occurrence of defects. So I would want to find out which inspection parameter or quality characteristic is actually contributing to a higher number of defects so that I can perform necessary root cause analysis and then look at arresting the occurrence of defects, right? So as a service provider, I'll be interested in knowing the defect count, but as a customer, I would be more interested in knowing the defectives count. In fact, I would want the accuracy percentage metric to be calculated from a defective perspective. So it's always binary. A sample unit can either be defective or non-defective, right? So I'm least bothered as to how many defects are identified in a defective sample unit. So the entire sample unit has been rejected as a defective. So as a customer, I will always look at this particular metric as a binary metric. So the sample unit is either defective or non-defective. And I would be interested in knowing the accuracy percentage calculated from a defectives perspective, not from a defects perspective. So I will let you know what is the advantage you carry when we actually calculate all these matrices from a defects perspective. But even before that, we need to understand a very important terminology pertaining to the process capability analysis of a discrete scenario called OFE. OFE, the full form is opportunity for error, right? So what is this OFE? OFE is nothing but the number of inspection parameters that we consider while inspecting a sample unit. So this could be either the inspection parameter or the quality characteristics. So which would define the overall quality of the sample unit, right? So the number of inspection parameters or the quality characteristics that we would consider for inspecting a sample unit. So that is what we call as OFE. So when I say opportunities for error, it's all about the opportunities that the employees will have to commit a mistake. So that is why it is called as opportunities for error. So when the employees are going to enter these four fields, so they have four opportunities to commit an error per sample unit. When the employees are going to enter some values, right, under these four fields, the employees have an opportunity or four opportunities for committing an error with regard to a single sample unit. But then you have already automated a particular inspection parameter. That will not be considered as an opportunity for committing a mistake. When you automate it, that means, no way people would be able to commit a mistake in that particular audit parameter or inspection parameter. So the number of opportunities for error pertaining to a particular sample unit will also get reduced. So that is why people would tend to go for automation, because they can make the process performance much more robust, and they can also bring down the opportunities for error significantly. In other ways, they would be able to simplify the existing process when they perform automation. So this OFE is very, very important terminology as far as process capability analysis of a discrete data is concerned. So what does the count of OFEs, signify? So that's the next question. So when you find the count of OFEs to be significantly high, say the count of OFEs is in hundreds or even thousands, then what can you tell about that particular process? So what this would actually indicate, the count of OFEs. So if you find higher number of OFEs for a process, then what can you tell about that process?
More chances.
More probability of errors.
Yeah, that's there. But what can you tell about that process? We have higher probability of committing error is absolutely true. But what can you tell about that process?
It's not lean.
Defective process.
No. Unless and until people commit mistakes, you cannot say that it's a defective process, right?
Okay.
It's not lean.
No, it's not lean, obvious. So we have so many opportunities for error. Obviously, the process is not lean, so it gives scope for committing lot of errors. But then what does that indicate, the count of OFEs? If the count of OFEs is going to be very high, so what it would actually indicate? It's not lean is quite correct, right? But then want the exact term, so what it would indicate. So when you are making the process lean, what exactly you're doing here?
Removing the waste.
Removing the waste. So what is that called as in terms of simplifying the process? You are making it much more simplified, correct?
Yeah.
So when you make it much more simplified, you are actually, reducing the number of opportunities for error. So higher the number of opportunities for error, it would indicate that the process is a complex process, correct? So the opportunities for error would actually indicate the complexity of a process. So if the process is highly complex, then obviously you will have a higher count of OFEs. So looking at the count of OFEs, you will be able to tell whether the process is a simple one or a complex one. But when we actually worked on all these improvements, whether it's Lean or Six Sigma, you should have ideally simplified the process, right? So after simplifying the process, obviously the count of OFEs should have got reduced. So you cannot have the same count of OFEs existing even after simplifying the process. That means you have not done any work, correct? So if you have actually simplified the process, made it lean, or you have applied some Six Sigma tools, then the count of OFEs should have got considerably reduced compared to the baseline scenario. So that is yet another indication that you have worked on the process improvements in a successful way, right? So the count of OFEs would indicate the complexity of the process, which we need to remember. Now let us look at a very simple example here. So let us make a comparison. So we have two different processes, tea making process and rocket launching process. In tea making process, I have identified 6 defects. Rocket launching process, I have identified 60 defects. Just by considering the defect count, can I say that tea making process is a better process than rocket launching process? Just by looking at the defect count, can I say that tea making process is a better process than rocket launching process?
Is it a defect count or OFE count?
No, it's a defect count. 6 defects were identified. So I'm comparing the performance of these two processes. Just by looking at the defect count, can I say the tea making process is a better process than rocket launching process?
No,
Why?
because we look for defective.
It's not a number of defective. It is about how many defects are
Yeah, how
also
many
there.
defects are there, but why are we not, or why we should not compare these two processes by looking at the defect count?
Total number of
We-
parameters would be higher in rocket launching.
Yeah, so the thing is, these two processes have varied complexities, right? So we cannot definitely compare the performance of these two processes just by considering the defect count, because the opportunities for committing errors will be pretty much high in a rocket launching process compared to a tea making process.
Yeah.
So just by looking at the defect count, it will be unfair for us to compare these two entirely different operations, correct? So
Yeah.
what we need to do probably, since it is the varied complexity of these two processes, which is actually preventing me from comparing their performances. So what I can do is I can calculate the defect rate by considering the OFEs, right? So in a tea making process, I might have identified 6 defects out of 10 opportunities for error. I'm just throwing some random number here. But in a rocket launching process, I might have identified 60 defects out of 6 lakhs opportunities for error. Because rocket launching process, we all know, is a highly complex process, right? So when we introduce OFE to provide weightage for the varied complexity of these two operations, then I will be in a position to compare the performance of these two entirely different processes. So tea making, the defect rate will be 6 out of 10. Rocket launching, it will be 60 out of 6 lakhs. So whatever defect rate we get for tea making and rocket launching, we would then be able to compare, because for the varied complexity, I've already provided the weightage by considering the number of opportunities for error for these two processes. So just by looking at the defect count, it will not be fair on my part to compare the performance of these two entirely different set of operations. But once I calculate the defect rate by considering the number of opportunities, which would actually provide weightage for the respective complexity of a process, then I would be in a position to compare the performance of two entirely different set of operations, right? So an insurance process will be or can be compared with an accounts process, or an engineering process can be compared with some service process. So two entirely different set of operations can be compared when we calculate the defect rate by considering the respective opportunities for error applicable for a particular process. Clear about the strength of OFE? So that is what I have summarized here in the notes as well. So the first I have given the distinction between the defects and defective. So defects are the errors identified at an audit or inspection parameter level, whereas defectives are always referred from a unit level. A defective unit can contain one or multiple defects in it, whereas opportunities for error is the number of audit or inspection parameters considered in a process. So OFE would reflect the complexity of a process. So calculating the defect rate by considering the OFE count of any two processes will help in comparison of the performance of these two different operations, right? So let us see, what are all the various process capability matrices that we have when we calculate it from a defects perspective as well as from a defectives perspective. And we'll also look at the advantage that we would have when we calculate all these matrices from a defects perspective, right? So the first metric that we have is DPU. So what is DPU? As it is explained here, this is defects per unit. DPU is defects per unit. So the formula is number of defects in the numerator divided by the total number of units inspected. So number of defects divided by the total number of units inspected. So in case of calculation of this metric pertaining to this example, so we have total of 5 defects identified out of 5 sample units. So it will be 5 divided by 5. So DPU will be 1. So that is what I have written here, right? The next metric that we have is DPO, which is called as the defect rate. So this is defects per opportunity, right? So this is number of defects again in the numerator divided by total number of units inspected multiplied by number of OFEs per unit. Total number of units inspected multiplied by number of OFEs per unit. So if you look at this particular example, how many total number of opportunities are there? So we have 4 opportunities for error per sample unit. But then we have 5 sample units,
20.
which have been inspected. So it will be 5 into 4. So we will have total of 20 opportunities for error, which would have been inspected by the quality inspection team. So if you have the total count, see here the total count will be displayed 20, right? So that will be part of my denominator when I calculate the DPO metric for this scenario. So for this particular example, the number of defects is again 5, but then we have 5 units and each unit having 4 opportunities for error. So 5 into 4, we will have total of 20 opportunities for error. So 20 will be there in the denominator. So 5 divided by 20, we get the value 0.25. And this is what we would call as the defect rate. And then the third metric that we have is DPMO. So this is something that we have already got introduced. So when we actually got introduced to Six Sigma, we even looked at this metric. DPMO is defects per million opportunity. Defects per million opportunities, right? And this is just an extrapolation of DPO value. So this is DPO multiplied by 10 to the power of 6 will give me DPMO. So DPO multiplied by 10 to the power of 6. So you don't have to inspect, say, 1 million parameters. This is a crude explanation I would have given when we got introduced to Six Sigma. So when we said that at Six Sigma level, a process would contribute just 3.4 defects per million opportunities. In order to explain that, I would have told you, suppose you are inspecting 1 million parameters, and if the inspection team is going to identify only 3.4 defects in these 1 million parameters, then your process is said to be functioning at that Six Sigma level or world-class level. But then, if you strictly see, DPMO is an extrapolation of DPO. So there is no need for us to inspect, say, 1 million parameters. So if you have the DPO value, so we can simply multiply that DPO value by 10 to the power of 6, and we will get DPMO. So DPMO is just an extrapolation of DPO. So 3.4 DPMO would translate into Six Sigma level, which is the world-class level, right? And finally, we will calculate the sigma level for this discrete scenario. So this sigma level calculation is totally different from what we saw yesterday. So yesterday we saw the sigma level calculation for a continuous data scenario, which is normal. So this sigma level calculation is for discrete data scenario, right? When we deal with defects and defectives. So the sigma level calculation can be done by applying an Excel formula, and the formula goes something like this, is equal to norm SINV open bracket 1 minus DPO plus 1.5. So this is the formula to be applied for calculating the sigma level for a discrete scenario. So we need to have the DPO value for us to calculate the sigma level, right? So these are the matrices that we would consider for ascertaining the process capability for a discrete scenario. But then if you are calculating the process capability from a defectives perspective, so whatever we saw, these are the process capability matrices calculation from a defects perspective. Again, when we calculate DPMO, so we will simply extrapolate this DPO value by multiplying it by 10 to the power of 6. So 0.25 multiplied by 10 to the power of 6 will give me 250,000, right? And for this DPO value, the equivalent sigma level will be 2.17, which has been calculated by applying this Excel formula. So for 0.25 as DPO, the equivalent sigma level will be 2.17, which has been calculated by applying this Excel formula. So this is the calculation done from a defects perspective, right? But when we calculate the same set of matrices from a defective perspective, now what will be DPU? Here the DPU will be called as defectives per unit. The formula, whatever we saw for defects calculation, is pretty much the same for defectives. Only thing is we'll be considering the count of defectives instead of count of defects. That's the only difference. So DPU again, here will be defectives per unit. So it will be number of defectives divided by total number of units. So how many defectives were identified in this example? 3 defectives were identified out of 5 sample units. So 3 divided by 5 will be my defectives per unit, right? And then we have defectives per opportunity, DPO. So there we considered each and every inspection parameter as an opportunity for error, because the defect is always referred from an inspection parameter perspective, right? But then defectives, as I told you, is always referred from a unit perspective. So when we consider a sample unit, the sample unit can either be defective or non-defective. The sample unit being defective, the opportunity will always be equal to 1, right? So the sample unit can either be defective or non-defective. The sample unit going as defective, the opportunity will always be 1, right? When we calculate from a defective perspective. And this is the main difference between the defects calculation and the defectives calculation. So that's why I told you, your customers would always, prefer the calculation done from a defectives perspective, because this is much more stricter calculation than the defects perspective, right? So when we calculate it from a defectives perspective, we need to remember the number of opportunities for error will be considered as 1, irrespective of the complexity of the process. The process can be highly complex, but the number of opportunities for error will always be considered as 1 when we calculate it from a defectives perspective, because we are looking at defectives from a unit angle. So a sample unit can either go as a defective or a non-defective. The sample unit being a defective, the opportunity is always considered to be 1, irrespective of the number of OFEs that you might have actually identified for a particular process, right? So that is why the defectives per unit will always be equal to defectives per opportunity. And this is the stage where the defectives, calculation becomes much more stricter, right? So here, when we calculate the same equivalent metric, which is DPO, defects per opportunity, we have the flexibility of considering the total number of opportunities for error, right? So we can, consider the total number of opportunities for error in the denominator. So when we increase the denominator, what will be the resultant output? Yesterday also we saw the resultant output is likely to decrease, correct? So the defect rate will definitely come down if you are going to increase the opportunities for error. Say, for example, instead of 4, you are going to make it 40. You're just adding one more cipher. So what will be my defect rate? It will become much more better, right? It will be 0.025. And you see the sigma level, it has drastically improved from 2.17 to 3.46. So what did I do? I just added one more cipher to the existing number of OFEs. That's it, right? So this kind of manipulation can be done when people calculate from a defects perspective. So the top management has to be quite vigilant, right? And this is what we would call as the denominator management in Six Sigma. So without even making any improvement, people can play around with the number of OFEs and they can simply hike the number of OFEs in the improved scenario and they can show a better picture, right? So 2.17 to 3.46 is a very good improvement, right? But then what people have done here, the people have simply increased the number of OFEs in the post-improvement scenario in order to show a better picture. So here people wouldn't have made any kind of improvement. So baseline scenario, the count of OFEs was only 4. The improved scenario, they made it as 40 and showed a better picture to the leadership, right? So leadership has to be quite vigilant when they review the project exercise and when they find that the project team has actually calculated all these process capability matrices from a defects perspective, they need to look at the count of OFEs. It has to be apple to apple comparison, right? So they would need to look at the count of OFEs. So what is the count of OFEs they have considered for the baseline and for the improved scenarios, right? That is very, very important. Otherwise, we can have a situation like the denominator management, right? So wherein people can simply, increase the count of OFEs and they can show a better picture. So the customer would not want to get into a debate or a discussion with regard to how many OFEs are there in a particular process, right? So for the customer, the sample unit is either defective or non-defective. That's it. So he's least bothered about the number of OFEs present in that particular process, right? So that is why the customers would always want you to calculate from the defectives perspective. Otherwise, people calculating from a defects perspective can always, show a better picture. Even otherwise, if you see, even if they had considered the exact number of OFEs applicable for a particular process, we still find a better defect rate than a defective, right? So that's an advantage because you consider, 20 in the denominator for calculating the defect rate, whereas you'll be considering only 5 as the denominator for calculating the defective rate, right? So that's the main difference. So people can definitely get a lot of advantage when they calculate from a defects perspective. Things will be very, very flexible and easy, and they can also show a better picture. But then as far as the customer is concerned, the customer would be more interested to know the calculations from a defectives perspective. And this is the stage where there is a huge difference between the defects calculation and the defectives calculation. And this is for the same scenario. We are not considering two different scenarios here, right? So zero point 0.6 will remain as defectives per opportunity. And from this value, we'll extrapolate and then arrive at PPM. So this is the equivalent metric for DPMO. So when I say DPMO, it is defects per million opportunity. So when we calculate the same metric from a defectives perspective, the metric will be called as PPM, parts per million. But the calculation is pretty much the same. So this is defectives per opportunity multiplied by 10 to the power of 6. And then we will calculate the sigma level finally by considering defectives per opportunity. So for the same process performance, we find the sigma level to be 2.17 when we calculate it from a defects perspective and the sigma level to be 1.25 when we calculate it from a defectives perspective, right? So this itself is a huge difference, correct? So 1.25 to 2.17 itself is a very big improvement, right? But then, we need to understand when we calculate the process capability from a defects perspective, we can always play around with the number of opportunities for error, which would actually provide us with necessary cushion, right? To hide all those, negatives in the process. We can still present a better picture to the management. So even if you are going to consider the actual number of OFEs applicable to that process, we would still have a huge advantage when we calculate it from a defects perspective compared to defectives perspective, right? But when you are provided with the number of defects for a case scenario, you don't have a choice but to apply the process capability matrices that are applicable for the defects, right? We'll always calculate it from a defects perspective. And that is exactly what we are going to see in all these three exercises that we are going to solve as part of the process capability analysis for a discrete data. So all these three formats are likely to come as questions in the final assessment, right? So, but then I've given the template. So you're going to apply the formula and perform all these calculations. Then, as I told you, I've given the template, right? So in case you find the uh, calculation logic slightly difficult to understand, you can always make use of the template. But then the final assessment, always go for the template. Even if you're aware of the calculation logic, just to save time, you can, use the template. Fine. So let us look at exercise number 1 under PC discrete. Out of 150 calls sampled, so this is a call center process. Out of 150 calls sampled, 22 defects were identified. The audit parameters per unit call is 8. Estimate DPU, DPO, DPMO, and sigma level. So since we have been provided with the defect count, so we need to apply the process capability matrices from a defects perspective. So first, let me summarize all these values. So how many calls have been audited here or sampled here? 150 calls.
150.
Yeah. So number of defects, 22. Number of OFEs. So what will be the number of OFEs for this scenario? So what is the count of OFEs? So which one we need to consider as count of OFEs?
115 to 8.
150.
That is a total number of OFEs. But OFEs per unit is the
8.
number of audit parameters that is given in the question, which is 8. Very good. So number of OFEs per sample unit is 8. Now, how will you calculate defects per unit? It will be number of defects divided by number of units audited, right? And DPO will be number of defects divided by number of units audited multiplied by number of OFEs per unit sample, right? And then what will be DPMO? DPMO will be DPO multiplied by 10 to the power of 6, right? And finally, we will calculate the sigma level applying the Excel formula is equal to norm S INV, open bracket, 1 minus the DPO value plus 1.5. So you get the sigma level as 3.59. So for this scenario, if you are applying the template, then we need to provide all these input values in the input section. So the count of defects, 22. How many calls were audited? 150 calls. How many opportunities are there per unit call? 8 opportunities are there. So moment we provide all these input values, you can see the answers getting populated in the output section. So DPO is 0.0183, DPMO is 18,333. The accuracy rate, which is 100% minus the defect percentage, right? So which is 0.9817. So this is 1 minus 0.0183, which will be 0.9817. And the sigma level is 3.5, right? So here the opportunities per unit and the number of units sampled have been given as a split. But sometimes, right, they would actually combine this together and they will provide you with the total number of opportunities, right? So they would have simply multiplied the number of samples audited and the number of opportunities per unit sample, and they would have provided total number of opportunities. So you can also get a question like this. So they would have given only the number of defects and the total number of opportunities. So in that case, how to use the template? So we just need to leave this number of samples audited field blank, and we need to provide the total number of opportunities here, right? That's it, right? You can leave the number of samples audited field blank, but then provide the total number of opportunities in this third field, the input section. You'll still get the same answer. So instead of giving the title as number of opportunities per unit, I will simply leave it as number of opportunities, because there can be a question wherein they would have provided the total number of opportunities by combining number of samples audited and the number of opportunities per unit sample. So they would have provided the total number of opportunities. So in that case, we need to update that value in the third column, right? You can leave the second field blank, number of samples audited field, right? But if they had given both number of samples audited and number of opportunities per unit sample, then we can fill in the data in all these three fields. Of course, the defect count will anyway be given. So this is how we will perform the calculation. So I can get multiple questions pertaining to this format in the final assessment. And then moving on to exercise number 2. So you can also get a question like this, wherein the sigma level for a process is given as 3.24. And we have been asked to calculate the defect percentage for this process. Very interesting question, right? So there, we actually obtain the sigma level at the end. Now, the end result has been given to us. And we need to go in the reverse direction to calculate the defect percentage, right? So when sigma level for a process is given as 3.24, so what is the formula that we would apply for calculating the sigma level? So the Excel formula is norm is INV, open bracket, 1 minus DPO plus 1.5. And this is given as 3.24, right? So DPO is the defect rate, as I told you. And that is exactly what we need to calculate. So whatever decimal value you'll get as a defect rate, that can be expressed in terms of a percentage value, right? But first we need to calculate the DPO value. So I apply the sigma level formula here, and this sigma level formula is the Excel formula, right? We already got introduced to it. And this is 3.24 as given in the question. Now what I'm going to do, I'm going to take 1.5 to the other side. Now it will be norm as INB, 1 minus DPO is equal to 3.24 minus 1.5. So what is 3.24 minus 1.5? 1.74. So norm S INB, open bracket, 1 minus DPO will be equal to 1.74. Now I'm going to take this norm S INB to the other side. So it will become 1 minus DPO is equal to norm S dist of 1.74. Norm S dist, inverse will become dist if it is taken to the other side. So what is this norm S dist? So is equal to norm dot S dot dist of 1.74 comma true, cumulative will be true. So the value is 0.9591 when we are rounding this off to 4 decimals, right? So 1 minus DPO, we get the answer as 0.9591. And 1 minus the defect rate is what we would call as the yield rate or the accuracy rate. 1 minus the defect rate is what we would call as the yield rate or the accuracy rate. So 0.9591 is the yield rate or the accuracy rate. In terms of percentage, this will be 95.91%. And this will be my yield percentage or the accuracy percentage. So what will be my defect percentage? So it will be 100% minus the yield percentage or accuracy percentage. Or in terms of decimals, this will be 1 minus the yield rate. So DPO will be You take DPO to the other side and you bring 0.9591 to the left-hand side. So DPO will become 1 minus 0.9591. So what is this? 1 minus 0.9591? It will be 0.0409. So DPO will be 0.0409 and the defect percentage will be 4.09% for this sigma level. So defect percentage will be 4.09% for this sigma level. But then if this is going to be slightly difficult to understand, you can always use the template that is given right below this exercise, wherein we just need to update the sigma level that's given in the question. That's it, right? That's the only value you need to update here. So this is 3.24 as given in the question. Just update that value and press enter. You'll get the answers, right? So the accuracy rate that we calculated 0.9591 or 95.91%, and the defect rate is 0.0409, or the defect percentage is 4.09%, and the number of opportunities that would lie outside the customer specification limits. So this is nothing but your DPMO value, right? So the DPO multiplied by 10 to the power of 6 will give you 40,930 for this scenario. So you might also be asked to calculate the number of opportunities that would lie outside the customer specification limits. So given the sigma level, you can be asked to calculate the number of opportunities that would lie outside the customer specification limits. In that case, we can pick the value from here, right? So third column in the output section. Or if they want you to calculate the defect percentage, you can consider the defect rate value, that is there the second column, this output section, and convert this in terms of a percentage value. Or if they want you to calculate the yield rate, then we can pick this one, 0.9591, and convert this in terms of the percentage value, right? We just need to update the sigma level alone. That's it. Rest of the things Excel will take care. So usage of this template is going to be very, very, very easy for you. So even in the future, right, even after the assessments are over, when you actually work on a project exercise, you don't have to feel the absence of Minitab software, right? So whatever Minitab will provide you, so the same set of output will be provided by this template. I've designed it in such a way that whatever output values you would get in a Minitab, right, the same set of output values will be provided by the template. In fact, these exercises can be solved only by applying the manual formula, right? You don't even use Minitab for solving all these things. So we'll apply only the manual formula to perform the calculations. But then when you're using the template, you don't have to really apply any of these formulas here. Fine. Exercise number 3. It's quite an interesting one. So the DPMO for a process is given as 860, and we have been asked to calculate the sigma level. So the DPMO for a process is given as 860, and we have been asked to calculate the sigma level. So we all know that the sigma level can be calculated from the DPO value. So we just require the DPO value for calculating the sigma level, but we have been provided with the DPMO value. So what I need to do, first I need to convert this DPMO value into DPO value. So for that, let me write the DPMO formula. So what is the DPMO formula? As we just now saw, it's an extrapolation of the DPO value. So DPO multiplied by 10 to the power of 6 will be my DPMO, right? And what will be DPO? So DPO will be DPMO divided by 10 to the power of 6. So take 10 to the power of 6 to the other side. Then we can derive this. DPO is equal to DPMO divided by 10 to the power of 6. So what is DPMO? DPMO is 860. So 860 divided by 10 to the power of 6 will be my DPO, right? So 0.00086. Now this value can be applied in the sigma level formula. So the sigma level will be is equal to norm SINB open bracket 1 minus DPO value plus 1.5. That's it. So round this up to 2 decimals. 4.63 is the sigma level for this process performance. But then if you're using the template, no need to actually convert this DPMO into DPO and then apply the sigma level formula to perform the calculation. We can straight away input the DPMO value here as given in the question and press enter. That's it. So you'll get to see what is the equivalent DPO and also the sigma level 4.6. Right? So you can also get a question like this, wherein they would have provided you with the DPMO value and they would have asked you to calculate the sigma level. So in that case, you need to use the template given under exercise number 3 in PC discrete. So if you look at the template reference, I have actually given this very clearly. So yesterday itself, we got introduced to that sheet, the template reference sheet. So till normal distribution we have seen, right? So next one is the process capability analysis for discrete. So as input values, the final assessment question, right? So you'll be provided with the number of defects, the number of samples audited, and number of opportunities, or as I told you, the total number of opportunities, wherein they would have combined the number of samples audited and number of opportunities per unit sample. And they would have provided you with the total number of opportunities. So with these input values, you'll be asked to calculate the sigma level, right? And we need to use the template under exercise number 1 in PC discrete sheet. So it will straight away take you to that place where the template is stored. And then the second scenario. So what is the second scenario? So you'll be provided with the sigma level, the same PC discrete. So you'll be provided with the sigma level and you'll be asked to calculate either the defect percentage or the yield percentage, or you might be asked to calculate the number of opportunities which might actually lie beyond the customer specification. So this is actually your DPMO value, right? So that being the case, we need to use the template given under exercise number 2 in the PC discrete sheet. This one, right? And then the third scenario, wherein they would have provided you with the DPMO value, right? The input value will be DPMO and they would have asked you to calculate the sigma level. So we need to use the template given under exercise number 3 in PC discrete sheet. Just click on that link. It will take you to the place where the template has been stored. Right? So this is about the process capability analysis for the discrete data. So next we are going to look at the process capability analysis for continuous data. So this is called continuous process capability analysis. And these process capability matrices that we are going to see for continuous data can be applied only if the data distribution is normal, right? Now you can understand what are all the various advantages that we will have when we find the data distribution to be normal, right? So when the data distribution is normal, as I told you, we have good number of statistical tools and techniques that can be applied for that scenario. But then when the data distribution is non-normal, as I told you, we have limited number of statistical tools and techniques that can be used for our analysis, right? So when we talk about continuous process capability, so we have 3 matrices under this. So CP is referred as the potential capability, CPK is referred as the achieved capability, and from this CPK value, we can also calculate the sigma level. So that's what I told you at the beginning itself. This sigma level is not a different one. So whatever we saw yesterday is the same sigma level. Only thing is we are going to calculate using a different methodology. So yesterday we used the conventional formula to calculate the sigma level, right, for a continuous data which is normal. But here when we are going to calculate the sigma level under process capability analysis, we are going to calculate the same from the CPK value. So CPK and sigma level are closely connected. So we are going to look at how to calculate the sigma level from this CPK value, right? So these are the three matrices that we have under continuous data process capability analysis. So let us look at all these matrices one by one, especially CP and CPK. So what we can actually understand, right? So since CP is referred as potential capability and CPK is called as achieved capability or the current capability. So we can clearly understand that CP as a metric will always be greater than or equal to CP, right? So the potential capability will always be greater than, or it can also be equal to CPK. So when you can perform up to your potential, then in that case, CP and CPK will be the same, correct? Say for example, there is a sprinter who can run 100 meters in 10.8 seconds. So this is the potential of that sprinter. On a given day, the sprinter might actually run 100 meters, say in 11 seconds. And that is his achieved capability, right? So what we can say is this sprinter has got the potential to run 100 meters in 10.8 seconds, but today he has actually run 100 meters in only 11 seconds, right? So the achieved capability here in this case is less than the potential capability. Or some other day, he can also perform up to his potential. So he can run 100 meters in 10.8 seconds, right? So he can always perform up to his potential. But then the achieved capability exceeding the potential may not be practically true, right? Even though, when we say, we will say that, he has achieved more than his potential. But then we need to understand, unless and until his potential has also increased, the person will not be able to achieve it. So when I say he has achieved, up to his or more than his potential, it automatically conveys that the potential has also increased up to that level, right? So we can always achieve up to our potential, but we cannot exceed the achieved capability, or the achieved capability cannot exceed the potential capability. So when we say, so for just for telling people, we can always say this, right? So we would have heard people telling he has achieved more than his potential. But what is the underlying fact here? Unless and until the potential has also increased up to that level, the person wouldn't have been able to achieve it, right? So the potential also would have increased up to that level. So what we can clearly understand through this is the potential capability, that is CP, will always be greater than or equal to CPK. So CPK, we can improve and make it equal to CP, right? That is what this particular statement clearly conveys. So first, let us look at the CP metric, then we will look at the CPK metric, and we'll also see how to calculate sigma level from that CPK value, right? So the first one, CP, is the potential capability, as I told you. The formula to calculate CP is USL minus LSL in the numerator divided by 6 times the standard deviation in the denominator. Now, what is this USL minus LSL? So USL minus LSL would indicate customer tolerance, right? So the customer actually provides the specification limits. So for nominal, the better kind of metric, the customer would have given both USL and LSL. So the distance between USL and LSL is something that is finalized by the customer. And that is what we would call as the customer tolerance. Why we call this as customer tolerance? Because if you have a unit product measuring anywhere between USL and LSL, the customer would be willing to accept that unit product as a conforming unit, right? So that is why the distance between USL and LSL will be referred as customer tolerance. That means the customer will be willing to accept a unit product with the measurement value falling anywhere between USL and LSL values specified. So it will be referred as customer tolerance. And what does this 6 into standard deviation actually indicate? 6 into standard deviation indicates the process variation. Because standard deviation, we all know, is a variation metric. So 6 into standard deviation would indicate process variation, right? So this is the CP formula. So customer tolerance divided by process variation. So let
What is
me
the
just,
significance of 6 here?
yeah, so actually, it's little bit technical, but let me just try to make you understand this. So you've already seen that, you know, the area coverage within 3 sigma limits is 99.73%, right? So
Hmm.
99.73% is approximated to 100%. 99.73% is approximated to 100%. So what is the distance? If you see, 99.73% is the area coverage between -3 and +3 for a standard normal distribution, right? So center will be the 0, correct? So what is the distance from 0 to +3? 3 units.
Yeah,
What is
okay.
the
Now it
distance from
makes
0 to -3? 3 units. 3 into
okay,
3,
okay,
6. So that is the
okay.
total width of the belt.
Okay,
So this is the logic, 6 into standard,
okay.
right? So let me just draw a couple of scenarios here. So let us try to understand this CP metric much better. So the first scenario looks something like this. So we have the LSL and the USL and the process spread, which is indicated by the width of the bell curve, is well within the specification limits, right? We have USL and LSL, and we have the process spread, right? Well within the specification limits. So what can you tell about this process? As we're looking at the diagram, what can you tell about this process? So only when we have the process spread extending beyond the specification limits, then we can understand that the process is contributing to non-conformances or defects. But here we have the process spread well within the specification limits. So what can you tell about this process? So when we construct a histogram and draw the bell curve, so we find the width of the bell curve well within the customer specification limits. So if the customer specification limits say vary from 9.8 to 10.2, just for example. So the process width could be from say 9.9 to 10.1. So what can you tell about this process?
Accuracy is within acceptable limit of customer.
Acceptable. So the process performance is well within the specification limits given by the customer. So 100% of the units produced by this process doesn't seem to be non-conforming to the customer specifications, right? So 100% of the units produced by this process seems to be conforming to the customer specification. So we don't see the width of the bell curve extending beyond the specification limits, is well within the specification limits. That means the entire production made by this process, they are adhering to the specification limits provided by the customer. So this could be any measurement dimension, right? So what we can tell about this process, we can say that this process is capable by design to meet the customer specifications, right? So here we have a scenario where the customer tolerance, which is nothing but the length of the, or is nothing but the distance between the specification limits, is much higher than the process variation, which is indicated by the width of the bell curve. Just now I explained, right? So this is indicated by the width of the bell curve. So we have a scenario where the customer tolerance is greater than the process variation. So when the customer tolerance is greater than the process variation, just by looking at this diagram, we can easily infer that this process is capable by design to meet the customer specifications, right? So if the customer tolerance is going to be greater than the process variation, then the CP formula, the numerator is going to be greater than the denominator, right? The CP formula the numerator is going to be greater than the denominator. So what will be the CP value for this scenario? If the numerator is going to be greater than the denominator, what will be the CP value? Mathematical logic. There is no calculation involved because we do not know what is customer tolerance, what is process variation. So just a mathematical logic that we need to apply here. If the numerator is going to be greater than the denominator in any formula, what will be the resultant value? Will it be less than 1 or greater than 1?
Greater than 1.
Greater than. This is the mathematical logic, right? So when you find CP to be greater than 1, we can easily infer that the process is capable by design to meet the customer specification. Right? CP being greater than 1, we can easily understand that the customer tolerance is actually greater than the process variation. So then only the CP value will be greater than 1. So if you find the CP value to be greater than 1, then we'll be looking at a scenario like what I have drawn here. So in that case, we can infer that the process is capable by design to meet the customer specifications. So there can be a question on this in the final assessment. So they would have given the CP value and they will ask you to infer. So if you find the CP value to be greater than 1, we need to pick the option the process is capable by design to meet the customer specifications. So let me draw the second diagram. So this is the second scenario. We have the LSL and USL. And we have the process spread extending beyond LSL and USL. Just by the look of it, what can you tell about this process?
Results found out of the tolerance.
Pardon?
Results found out of the limits.
Yeah, it's going outside the specification limits, right? So this process would be contributing to non-conformances or defects. So the area that falls outside the specification limits for this process diagram is what I have shaded. So the shaded area would actually signify the non-conformance or defects produced by the process. So here you find the customer tolerance, which is the distance between USL and LSL, is actually less than the process variation, which is indicated by the width of the bell curve. So here we find the customer tolerance to be less than the process variation. And in the CP formula, the numerator is less than the denominator. What is the likely CP value? Will it be greater than 1 or less than?
Less than,
Numerator is less than the denominator. What will be the resultant CP value?
less than 1.
Less than, right? So if you find the CP value to be less than 1, what is that we can infer? We can infer that the process is not capable by design to meet the customer specifications, right? So CP value greater than 1, you can infer that the process is capable by design to meet the customer specifications. On the other hand, if CP value is less than 1, then we need to infer that the process is not capable by design to meet the customer specification. So why the process is not capable? Because when CP is less than 1, we can easily understand that the customer tolerance will be less than the process variation. If the customer tolerance is less than the process variation, then the process is likely to contribute to non-conformances or defects, right? So that is why we say when CP is less than 1, the process is not capable by design to meet the customer requirements or specifications. And that is what I have given here. So if the customer tolerance USL minus LSL is greater than the process variation, which is 6 times the standard deviation, the resultant CP value will be greater than 1, which would indicate that the process is capable. On the other hand, if the customer tolerance USL minus LSL is less than the process variation, then the resultant CP value will be less than 1, which would indicate that the process is not capable by design to meet the customer requirements. So this scenario will be asked as a question in the final assessment. So they would have provided you with the CP value and they will ask you to make the relevant inference. So if you find the CP value to be greater than 1, we need to pick the option the process is capable by design to meet the customer specification. If you find the CP value to be less than 1, then we need to infer that the process is not capable by design to meet the customer requirements. So let me just make this in bold font so that you can easily pick the answer from here, right? So we will have a 50-minute break now. So when we come back, we will look at the CPK metric, the importance of the CPK metric and how to calculate sigma level from that CPK value. So that will be after a 15-minute break. Hello, friends. I'm back. Hope you're all back as well. So before the break, we were discussing about the CP metric, which would represent the potential capability of a process. And so the CP metric will always be greater than or equal to CPK. So when achieved capability or the current capability is equal to the potential capability, then CP will be equal to CPK. But then you might have a scenario where the achieved capability or the current capability could be less than the potential capability. In that case, the CP will be greater than the CPK. But then if you look at CP as such, it is derived by using the formula USL minus LSL divided by 6 times the standard deviation. So USL minus LSL would represent the customer tolerance, and 6 times the standard deviation would represent the process variation. But then if the customer tolerance is going to be greater than the process variation, then the resultant CP value will be greater than 1, which would indicate that the process is capable by design to meet the customer requirements. On the other hand, if the customer tolerance is less than the process variation, then the resultant CP value will be less than 1, which would actually indicate that the process is not capable by design to meet the customer requirements. So what I'm going to do, I'm going to draw some 3 process scenarios, and let us calculate CP for all these 3 process scenarios and try to understand what is the drawback with this CP metric. So the first process scenario is something like this. So we will have the LSL and USL. So LSL is 30, USL is 40, and we have the process spread well within LSL and USL with the process mean exactly aligning with the target. So 30 is LSL, 40 is USL. So what will be the target? Target will be 35, the midpoint between LSL and USL, as we understood yesterday. And the mean here is aligning with the target because mean is also 35 and the standard deviation is 1. So this is the first process. The second process, the same LSL and USL, 30 and 40, and we have the process mean also 30. X bar is also 30. So which means 50% of the process diagram is actually falling outside the lowest specification limit, right? So 50% of the process diagram is actually falling outside the LSL, which means there's only 50% adherence to the customer specification because we find only 50% of the process diagram between LSL and USL. So 50% is falling outside the lowest specification limit, which will be the non-conformance or defects, right? And the third process scenario, the same LSL and USL, 30 and 40, but then we have the process diagram way below the LSL and the process mean is 25. But the standard deviation continues to be 1 for all the 3 scenarios, right? So if you look at the third scenario, 100% of the production doesn't seem to be conforming to the customer specification. So the entire process diagram is way below the LSL, which would mean that 100% of the production, right, doesn't seem to be conforming to the customer specification. So out of these 3 process scenarios, which one is the best in class process? Out of these 3 process scenarios, which one is the best in class process?
Number one.
Number 1, without any doubt, right? So number 1 is the best in class process. But then if you compare the second process and the third process, then we can say that second process is comparatively better than the third process. But the second process is also not performing well. So 50% non-conformance is not a good thing, right? So second process is also performing really bad. But when we compare it with the third process, we can say that second process is comparatively better than the third. That's all. But then let us calculate the CP value for all the three processes. So what is the CP formula? The CP formula is USL minus LSL in the numerator, which is 40 minus 30 for this scenario, divided by 6 times the standard deviation, divided by 6 into 1, right? Standard deviation value is 1. So you get the CP value as 1.67, right, for the first scenario, which is absolutely fine because we could actually notice that the first scenario has this process spread well within the specification limits, and we also find the mean to be aligning with the target, and the standard deviation is also very, very low. So this is a best in class process, and CP value being 1.67 doesn't even surprise us, right? So CP value is quite apt. So anything greater than 1, we can say that the process is capable by design to meet the customer requirements. So let us calculate CP for the second scenario. So again, CP will be 40 minus 30 in the numerator divided by 6 into 1. So you'll get the same 1.67 even for this second scenario. And when we calculate CP for the third scenario, again apply the formula 40 minus 30 in the numerator divided by 6 into 1. So CP will be 1.67 for the third scenario as well. So what is the drawback with CP? So as we can see, CP doesn't consider positioning of mean, right? So in the CP formula, you don't even find the mean metric evident, right? So CP considers only the standard deviation along with the customer specification limits, right? So it doesn't even consider the positioning of mean. So the second and third scenario, what we can understand is these two processes have the potential to perform like the first process. The second and third processes have the potential to perform like the first process. So what is the adjustment that we need to do? So we need to move the mean and make it align with the target. So both second and third process scenarios, we need to shift the mean and make it align with the target. So that would help us to improve the process performance like the first process scenario, right? So CP of 1.67 for the second and third processes indicates that these two processes have the potential to perform like the first process, but their current performance is not all that good. But if you want to ascertain the achieved capability or the current performance of the process, then we need to calculate CPK, right? So CPK and sigma level would help us to achieve the current performance or the achieved capability of the process, right? So once we have the CPK calculated for all these three process scenarios, we will be able to clearly differentiate these three process scenarios based on their current performance, right? And that is what we are going to do next. But before that, let us try to understand how to calculate the CPK value. So as I told you, CP as a metric would just indicate the potential capability of a process, and we will not be able to understand what is the current capability or the achieved capability of a process because CP as a metric doesn't even consider positioning of mean. So hence we need to calculate CPK and sigma level to understand the current capability or the achieved capability of a process. So how to calculate CPK? So the formula that I have given here is pretty much similar to our Six Sigma formula that we saw yesterday, right? So the formula for CPK as it is given here looks to be somewhat similar to the sigma level formula that we saw yesterday. So CPK is also minimum of mean minus LSL divided by 3 times the standard deviation. For sigma level, the denominator will be just the standard deviation. But for CPK, it will be 3 times the standard deviation. So that's the only difference. Or USL minus mean divided by 3 times the standard deviation. So if you are going to take 1 by 3 outside, then CPK will be 1 by 3 into minimum of mean minus LSL by standard deviation or USL minus mean divided by standard deviation. So what is this part of the formula? So CPK will be 1 by 3 into sigma level, right? So this is the sigma level formula that we saw yesterday. So our sigma level can be written as 3 times the CPK. So that's what I told you. We can also calculate sigma level from the CPK value. So 3 times the CPK value will be your sigma level. So once we calculate the CPK and sigma level for all the 3 process scenarios, we would be able to clearly differentiate the current performance of these 3 processes. So let me calculate CPK for the first process scenario. So for calculating the CPK, we need to find out whether the mean is aligning with the target or not. If it is aligning with the target, as I told you yesterday, we can apply either the LSL side formula or the USL side formula to calculate the CPK. But if mean is not aligning with the target, then we need to find out to which side the mean is actually tilting towards, and we need to apply that relevant side formula to calculate the CPK value, right? So the first scenario, mean is actually aligning with the target. So we can apply either the LSL side formula or the USL side formula to calculate the CPK value. So let me apply the USL side formula for calculating the CPK value. So what is the USL side formula? Similar to our sigma level formula, 40 minus USL minus mean, which is 40 minus 35 in the numerator divided by 3 into the standard deviation in the denominator. So we also get CPK as 1.67. So here is the scenario where CPK's performance is up to the CP level, right? So CP and CPK are pretty much the same. So when can CPK perform like CP? Only when mean is aligning with the target. So this is the learning from this first process scenario. So when will be the CPK equal to CP? When mean is actually aligning with the target. So when mean is equal to target, the CPK will be equal to CP. So there is no need for you to calculate CPK separately. So if the mean is aligning with the targets, it's enough. If you are calculating the CP value, the same CP value can be replicated as CPK. So you don't have to calculate CPK separately, right? So mean aligning with the target, the CPK will be equal to CP. And then we can calculate the sigma level from this CPK value. So sigma level will be 3 times CPK. So 3 into 7, 21, 2, 3, 6, 18, 19, 20, 2, 3, 1, 3, 4, 5. So sigma level is 5.01. So when we look at CPK and sigma level, we can clearly understand that the current performance of this first process scenario is actually excellent. Sigma level of 5.01. It's a very good sigma level score, right? It's an excellent score. Now let us look at the second scenario and let me calculate CPK for this. So what will be CPK? Now here is the scenario where mean is not aligning with the target. The mean is actually, tilting towards the LSL side. In fact, it is aligning with the LSL, right? Mean is aligning with the LSL. So obviously we need to apply the LSL side formula to calculate CPK. So what is the LSL side formula? Mean minus LSL in the numerator. So mean is 30, LSL is also 30. So it will be 0. So CPK will be 0. So 0 divided by any value will be 0. So CPK will be 0 and sigma level also will be 0, right? So here we can clearly understand when mean is aligning with one of the specification limits, so we will have only 50% adherence. When we have 50% adherence, the sigma level will be equal to 0, right? So yesterday we saw when we discussed about the area coverage under various sigma limits, when we have 68.27% adherence, what will be the sigma level? It will be 1, right? But when we have only 50% adherence, the sigma level will be equal to 0. So this is yet another learning for us. So when mean is aligning with one of the specification limits, the CPK and the sigma level will be equal to 0. So when mean is aligning with one of the specification limits, we can understand that only 50% of the production would be adhering to the customer specification. So when we have only 50% adherence, we can understand that the sigma level will be equal to 0. When we have 68.27% adherence, we understood yesterday that the sigma level will be equal to 1. But then when we have less than 50% adherence to the customer specification, the sigma level will be negative. And that is what we are going to see for the third scenario. So if you are calculating CPK for the third scenario, so which formula we need to apply here? So since the mean is actually gone past beyond this LSL, so we need to apply the LSL side formula to calculate the CPK value. So the LSL side formula is mean minus the LSL divided by 3 times the standard deviation, which will be minus 1.67. So this is exactly opposite to the first process scenario. So CPK will be minus 1.67. And sigma level, as we expected, will be in negative. So this will be minus 5.01, right? So when we calculate CPK and sigma level, we will be able to clearly understand the current performance of the process, right? And CPK and sigma level clearly demonstrates the current process scenarios for all these three processes. So the first one, as we all know, is the best-in-class process. So obviously the CPK is performing up to its potential, that is up to CP, and we also have a healthy sigma level. But then the second process scenario where the mean is aligning with one of the specification limits, the CPK and sigma level both will be equal to 0, right? So the third process scenario where mean is falling outside the specification limits, the CPK and sigma level will be negative. But then we need to understand that both second and third process scenarios can really perform like the first process, provided we are able to move the mean and make it align with the target. Because standard deviation is looking good, right? With respect to the customer tolerance, the standard deviation is good. That is why we have a healthy CP value even for the second and third scenarios. But then the current performance is not all that great because the positioning of the mean is not proper. So what we need to do, we need to make the mean align with the target. So second and third process scenarios, the second objective of Six Sigma has been fulfilled. That is, reduce the variation. The standard deviation looks good, right? Comparatively with the specification limit or the tolerance limits provided by the customer. But then what is lacking here? The positioning of mean is not proper. So the first objective has to be fulfilled. That is, align mean with the target. If that is done, then the second and third process scenarios can also perform like the first process scenario. And that is exactly what I have mentioned here. When mean is equal to target, then your CPK will be equal to CP. So this is the learning that we got from the first process scenario. But then when mean is equal to one of the specification limits, both CPK and sigma level will be equal to 0. So this is the scenario wherein only 50% of the process production will be adhering to the customer specification. So 68.27% adherence will be 1 sigma level. 50% adherence will be 0 sigma level. And the third scenario, when mean is positioned outside the specification limits, both CPK and sigma level will be negative. So this is a scenario wherein we will have less than 50% adherence to the customer specification. So what we need to do in order to improve CPK up to CP level? So if you want to improve CPK up to CP level, we need to align the mean with the target. So if you want to improve CPK up to CP level, then we need to align mean with the target, which is the first objective of Six Sigma. But then if you want to improve CP as such, right? So CP itself is less than 1. And if you want to improve CP as such, then what is that we are supposed to do? We need to look at reducing the variation. Reducing the standard deviation value alone will help us to improve the CP performance, which is the second objective of Six Sigma. So both the objectives of Six Sigma, right, are very much relevant as far as a process performance is concerned. So we will be able to improve CPK up to CP level by having the mean aligned with the target, and we will be able to improve the CP as such by reducing the variation, right? So let us look at an exercise under continuous data process capability analysis. In fact, we are going to look at the same problem that we solved yesterday under normal distributions, right? The same problem that we solved yesterday under normal distribution. So we will calculate the CP and CPK values for that scenario. And from the CPK value, we'll also calculate the sigma level, right? And see whether we are getting the same sigma level that we got yesterday, right? So let us also make that comparison. Fine. So this is the same problem, only difference is we have been asked to calculate the CP, CPK and sigma level for this process scenario. So you can get multiple questions in the final assessment asking you to calculate CP, CPK values. So you can use the same template that we saw yesterday under normal distribution. So same normal distribution template can be used for calculation of CP and CPK. So yesterday itself we also got the CP, CPK values displayed right in that template, correct? So I told you, since we have not yet, seen the CP and CPK matrices, so let us not even look into that. We'll only restrict ourselves to the yield rate or the defect rate and the sigma level. But now that we know what is CP and CPK, so we will use the same normal distribution template and perform the calculations, right? So the length of a unit product is normally distributed with a mean 32.3 centimeters and standard deviation 0.2 centimeters. So if the customer specifications are 32 to 33 centimeters, we have been asked to estimate CP, CPK and sigma level, right? So let me just summarize all these values. So what is USL given in the problem? 33. And what is LSL? 32. What is mean? 32.3. And we know that the mean is not aligning with the target. So USL is 33, LSL is 32. The target will be 32.5. And we know that the mean is not aligning with the target. So if you want to calculate CPK value, so we need to consider the LSL side formula for calculating the same, because yesterday itself we saw the mean was actually tilting towards the LSL side. So target being 32.5, 32.3 will be to the left-hand side of this target value. So if it is to the left-hand side of the target value, we can clearly understand that the mean is actually tilting towards the LSL side. So we need to apply the LSL side formula to calculate the sigma level. So mean is not aligning with the target and is tilting towards the LSL side, right? And is tilting towards the LSL side. Fine. What is the standard deviation? Standard deviation is 0.2. So how will you calculate CP? So CP will be USL minus LSL in the numerator divided by 6 times the standard deviation in the denominator. So USL minus LSL divided by 6 times the standard deviation in the denominator. So we get a CP value of 0.83. So what this would actually indicate? So since CP is less than 1, what will be your inference? We can infer that the process is not capable by design to meet the customer requirements. You can straight away infer by looking at the CP value. So CP value being less than 1, so we can straight away infer that the process is not capable by design to meet the customer requirements. Now what will be CPK? So CPK obviously will be a value less than the CP value, right? So CPK will be obviously less than CP because the mean is not aligning with the target. So mean is moving away from the target, either on the left hand side or on the right hand side. We will find the CPK value to be less than the CP value. So as I told you, for calculating CPK, we need to apply the LSL side formula. So what is the LSL side formula? It is mean minus LSL divided by 3 times the standard deviation. 3 into 0.2. So mean minus LSL divided by 3 times the standard deviation. So you get the CPK value as 0.5, right? So 0.5 obviously less than 0.83. So CPK is less than CP because mean is not aligning with the target. CPK is less than CP since mean is not aligning with the target, or the process is not a centered process. Now what will be the sigma level? Sigma level will be 3 times the CPK value. So 3 into 0.5 will give you 1.5. And this is the sigma level that we got yesterday as well when we solved the same problem under normal distribution. If you see, for the first scenario, the sigma level was 1.5. So you'll not get a different sigma level. The thing is the calculation methodology is different. So there, yesterday we applied the conventional formula to calculate the sigma level. So here we are calculating sigma level through CPK value. Now, the same assumption let us make today as well. So we assumed yesterday that the improvement has been done and the team has successfully fulfilled the first objective of Six Sigma. So the new mean will become 32.5. So with this new mean, what will be the improved performance that we can actually witness? So the same assumption is being made here as well. So let us assume that the first objective of Six Sigma is fulfilled and we have successfully aligned mean with the target, and hence the new mean will be 32.5. So with this new mean, what will be the process capability metric performance? So CP will not have any change. You will not have any change for CP, right? So CP will change only when the standard deviation changes. So the change in mean, you will not have any impact on this CP value, right? The CP value will remain the same. So it will be USL minus LSL in the numerator divided by 6 times the standard deviation in the denominator, same 0.83. But what will be the CPK value? Anyone? What will be the CPK value? CP is 0.83. So what will be CPK for this improved scenario?
It will increase.
Yeah, it will obviously increase, but to what extent?
More than one.
1.67.
No, CP is only 0.83, right? So how can CPK be greater than CP? It cannot go beyond 1, correct? So CP is only
Can be
0.83.
less than
So,
or equal to 8.83.
No, 0.83 is the
no,
answer.
less than or equal to, you are giving two options. What is the correct one? Will it be less than 0.83 or equal to 0.83?
Equal to 0.83.
It will be equal to 0.83, right? So I've told you, when mean is aligning with the target, the CPK's performance will be up to the CP level. So both CP and CPK will be the same. So CPK also will be 0.83. So you don't even need to calculate. So CPK cannot go beyond this, right? So CPK can only perform up to the CP level. So it cannot be greater than 1 or it cannot be 1.67, right? So it can perform only up to the CP level. There, in that scenario that we saw, the CP was 1.67. So when mean was aligning with the target, CPK also was 1.67. right? But then here we have the CP value itself as 0.83. So when mean is aligning with the target, the CPK can also become 0.83. It cannot go beyond that. So let us calculate and see whether this assumption is correct. So we will calculate CPK value separately. So we don't have to calculate. We can replicate the CP value as CPK, but still let us validate and see. So I'm going to use the USL site formula to calculate CPK. So what is the USL site formula? USL minus the new mean, which is 32.5 divided by 3 times the standard deviation, which is 0.2. So get the same 0.83 as CPK. That's what I told. So CPK has improved up to CP level since mean is now aligning with the target. So CPK has improved up to the CP level since mean is now aligning with the target. Now what will be the sigma level for this? It will be 3 times the CPK. So 3 into 0.83, which is 2.5. And we got the same 2.5 as the sigma level for the improved scenario yesterday as well. Right? Sigma level is. So this is now we need to perform the calculations and make necessary inferences. So as I told you, we can use the same normal distribution template for calculating the CP and CPK values. Let me input all the values here. So the sample mean for the first scenario, 32.3. Sample standard deviation is 0.2. LSL is 32. USL is 33. We should not forget to choose the right option here, both LSL and USL. So you'll get to see the CP value, which is 0.83, CPK is 0.5, and the sigma level is only 1.5. But then if you are going to align mean with the target, so the new mean becomes 32.5. So in that case, you can see the CPK improving up to CP level. So you don't see any change in the CP value, but CPK has improved up to CP level, and the sigma level has also parallelly improved to 2.5, right? And I have told you that mean aligning with the target is the best position for mean, wherein it can also provide its best performance. And that is the first objective of Six Sigma as well. So mean aligning with the target, we will be able to improve the sigma level up to 2.5. But if you want to improve the sigma level beyond this 2.5, because the CP is not looking good, it is still less than 1, which would indicate that the process is not capable by design to meet the customer requirements. So that being the case, we need to look at reducing the variation, which is the second objective of Six Sigma. So by reducing the variation, we will be able to improve the CP performance and take it beyond that one level. The CPK also will improve up to the CP level because the mean is already aligning with the target. So CPK also will parallelly improve along with CP. You don't have to really worry about improving the CPK metric, right? So CPK will also parallelly improve along with CP because the mean is already aligning with the target. So when we are reducing the variation, you will find the CP value improving and the CPK also parallelly improving along with CP. And we will see a corresponding improvement in the sigma level as well, right? So sigma level also will go beyond 3 level. So we'll see a corresponding improvement in the sigma level as well. So this is the entire process capability calculations, right? For a continuous data scenario. So aligning mean with the target, we will be able to achieve when the CPK or when we align mean with the target, we can improve the CPK performance up to the CP level. But if you want to improve CP as such, then we need to look at reducing the variation. This is the second objective of Six Sigma. So by reducing the variation, we will be able to improve the CP level as such. And when the mean is already aligning with the target, the CPK performance will also improve parallelly, and we will see a corresponding improvement in the sigma level as well. Right? So this is about the continuous data process capability analysis. Calculation of CP, CPK and sigma level. Now, at the end of the measure phase, what we need to understand is we will be coming up with the baseline sigma level of the process, right? So we would have calculated the baseline CTQ metric performance, and we will also arrive at the baseline sigma level. Now, keeping this sigma level, we will see to what extent we are supposed to improve, right? So that we will focus in the coming phases. So the next phase, that is the analyze phase, we will look at identifying the causes and the root causes for the business problem. So far in the define and measure phase, so we wouldn't have discussed anything about the causes or solutions, right? So our focus was completely on the business problem and the related CTQ metric performance. So at the end of the measure phase, we would have arrived at not only the baseline CTQ metric performance, but also the baseline sigma level, right? So that is very, very important. So in the analyze phase, we will start focusing on identification of causes and root causes. But before that, let us do a quick revision of the measure phase concepts because it's slightly a lengthier phase, right? And we covered a lot of things under measure. So if you look at Six Sigma, so measure phase will always be slightly lengthy, right, compared to the other phases, because we have a lot of things to learn in this measure phase. And measure phase is where we also got introduced to the statistical concepts, right? So that being the case, we worked out quite a good number of exercises as part of the measure phase. So let us do a quick revision before we move into the third phase in the DMAIC approach, which is the analyze phase. So the measure phase, we started by understanding what is data. So data, as we could see, is the numerical expression of any activity. So without data, there can be any number of opinions or perceptions about a process performance. But with data, there can be only one conclusion. But we also understood that the data should be unbiased. So if you are dealing with a biased data, then it would lead us into a GIGO situation, garbage in, garbage out kind of a situation. And then the project team will have to prepare this document called data collection plan. And the data collection plan will be approved by the leadership. And once it is approved by the leadership, this data collection plan document will serve as an approval document for the process team lead to hand over necessary data to the project team representative. So what are all the various elements that we can find in a data collection plan? The first one, so we are supposed to identify the CTQ metric along with the operational definition. So operational definition is nothing but the calculation logic that we are going to adopt for calculating the CTQ metric performance. And then we need to identify the baseline period for which the base data for the CTQ metric needs to be collated. And I have told you that we need to consider the latest 1 year period as the baseline period. And we need to identify the time frame during which the project team representative will visit the process team and collect the data. And then we need to identify the project team representative who would be visiting the process team to collect the data. And we need to identify the source of the data collation, whether the data is to be compiled from a Excel format or whether the data can be pulled out as a report from a workflow tool. And the final one, we also need to identify the appropriate graphical format that we will use for representing the CTQ metric performance. And then we looked at the types of data. So data, as we could see, is broadly classified into two types. So one is the discrete data and the other one is the continuous data. So discrete data is a count data which can be expressed only in terms of whole numbers. So it will not make any sense if you are going to express discrete data in terms of decimals or fractions. For example, number of participants, number of units processed, number of defects, etc. Whereas continuous data is a measured data which can be expressed in decimals or fractions apart from whole numbers. Example, length of a product, weight of a product, time taken to produce, cost of a product, etc. So when we classify a data as a discrete or continuous data, so we would be looking at the raw data, not a derived data. So which one you would call as a derived data? The data that is derived by applying a formula. So here, when we perform this classification of whether a data is discrete or continuous, we are not looking at any value which is derived by using a formula. So we are looking at a raw value and then performing this classification. Clear? Right? But then the clue that I gave you. So we need to look at the unit of measure. So the unit of measure cannot be broken into different levels. Then the data would be discrete. If the unit of measure can be broken into different levels, then the data will be continuous. But then under discrete, we have what is called binary discrete data. And this binary discrete data will have only two options for a result. And the best way to represent this binary discrete data will be in terms of proportions. So proportion, as we can see, is not a raw value, it is a derived value. So proportion can be derived by applying a formula containing a numerator and a denominator. So proportion will be expressed in terms of decimals. Just because you find the proportion value in decimal, you cannot straight away classify it as a continuous data. So we need to look at the formula which has been used for deriving this proportion value. If the formula fulfills these three conditions, then the proportion value will be considered as binary discrete data. So what are the three conditions? Both numerator and denominator in that formula should be count discrete. Numerator should be a subset of the denominator, which means it should be a part of the denominator, and there should be only two options for a result. So if these three conditions are fulfilled, then that proportion value will be considered as binary discrete data, and the metric for which the formula was applied will be considered as binary discrete metric. So we also looked at some three examples under binary discrete data: fast proportion, accuracy proportion, and the percentage time adherence to target. So proportion is the primary metric for expressing binary discrete data. Average is the primary metric for representing count discrete data. So when we have a count discrete data set, so we will calculate average by summing up all the count discrete values divided by the total number of data points. But average, as we can see, is also a derived value and can very well come out in terms of decimals. So if you are going to get the average value in terms of decimals for a count discrete data set, then what is that we need to do? We need to round it off to the nearest whole number. But then if you are calculating average for a continuous data, even if you get the average value in decimals, you can retain the same decimal value as it is, right? There is no need for us to round it off because continuous data can take decimal value. And then we stepped into the statistics part. So we looked at the descriptive statistics measures, two categories here: measures of central tendency or location, which is also called as measures of average. Under that, we have mean, median, and mode. So mean is a simple arithmetic average and is also very easy to calculate. But the problem with mean is that it would easily get influenced by the presence of outlier or extreme value in a data set. So hence, mean as a metric cannot be used if you find the presence of outlier or extreme value in a data set. So in case of any outlier or extreme value present in a data set, we need to use the statistical metric called median. So how to calculate median? Manually, So we need to first arrange the data set in an ascending or descending order and pick the central value. But then if you have two central values, if you have even number of data points, we will have two central values, and the average of these two central values will be considered as median. But then if you are applying the Excel formula, then there is no need for us to arrange the data set in an ascending or descending order. And also, if you have even number of data points, there is no need for us to, pick the two central values and calculate the average. So Excel will take care of all these calculations and it will provide the final answer for median. And then the third metric is mode, which is the most frequently occurring data point in a data set. So mode as a measure of average can be applied when we are dealing with the rating data or a rank order data set, right? So we also have the measures of variation. So again, three measures under this. Range. So range as a measure of variation is very easy to calculate, and it is the difference between the maximum and the minimum values in a data set. So the problem with range is that it doesn't consider any other value in between the maximum and the minimum values for its calculation. And hence range as a measure of variation can be applied only if the data set contains 6 or less than 6 data points. So if your data set contains more than 6 data points, then we need to use either variance or standard deviation. So both variance and standard deviation would represent the average distance of each and every data point in the data set from the mean value. So you already seen when we discussed about the concept of variation. So variation is simply defined as the deviation from the standard. So here the standard is nothing but the mean value. So the deviation of each and every data point from the mean value is what we would call as variance or standard deviation. And we also understood both variance and standard deviation cannot take negative values, and the least value that these matrices can take is 0, provided all the data points in the data set are same. And standard deviation, as we could understand, is a simplified version of variance. So the base calculation is pretty much the same, but standard deviation, we will go one step further. So we will take the positive square root of the variance value, and that will be considered as the standard deviation. And we also looked at how to apply the Excel formula to perform the descriptive statistics measures calculation. And then we looked at the graphical representation of data. The first graphical format that we looked at was histogram. So histogram is the appropriate graphical format to represent continuous data. So in a histogram, we will have both x-axis and y-axis. So along the x-axis, we will have the class intervals for the continuous data. And along the y-axis, we will have the scale for the frequency distribution. And this frequency distribution is nothing but the number of data points in the data set that would fall in a particular class interval. So once we have the frequency distribution calculated for each and every class interval, we will construct adjoining bars for these class intervals coinciding with their respective frequency distribution for which the scale is given on the y-axis. So once we have the adjoining bars constructed, we can connect the midpoints of all these adjoining bars, and if we get a symmetric bell curve, we would call the data distribution as normal. But then we can also get a skewed bell curve, that is a bell curve with a longer tail either on the right hand side or on the left hand side. So if the bell curve has a longer tail on the right hand side, we will call that as positively skewed, which can happen if the outlier value is on the upper side of the data spectrum. But if you have a bell curve with a longer tail on the left-hand side, we will call this as negatively skewed, which would mean that the outlier value is on the lower side of the data spectrum. So only if we get a symmetric bell curve, we will call that distribution as a normal distribution. But if you get a skewed bell curve, we will call that distribution as a non-normal distribution. And the three things that we can identify by looking at the histogram is the spread of the data distribution, the shape of the data distribution, whether it is normal or non-normal, and the class interval that is likely to contain the average value. So the class interval with the tallest bar is likely to contain the average value. But then the only drawback with histogram is that it wouldn't be able to capture the time orderliness of the data points. But then we have bar chart, which is the appropriate graphical format to represent discrete data, and pie chart is the appropriate pictorial format to represent proportions. And then we looked at run chart, and we could understand that line chart is the simplest form of a run chart. So line chart as a graph will be used if you want to depict a process performance over a period of time. So if you have the time zone along the x-axis, irrespective of the data type, we can use line chart to depict the process performance over a period of time. So the time zone, as I told you, can be on an hourly basis, can be on a daily basis, can be on a weekly basis, or it can be on a monthly basis as well, right? So if you have, or if you want to depict a process performance over a period of time, then the best representation will be the line chart. But then run chart, as we could see, is a sophisticated format of a line chart, which will also, contain the average line at the center. But then run chart, the primary objective is to validate whether the data distribution is random or non-random. So the data distribution is random. We can infer that the process is influenced by common cause variation alone, and the process performance is also stable or consistent. So we will be able to apply Six Sigma tools and techniques only if the process performance is stable or consistent. On the other hand, if the data distribution is non-random due to any of the four non-random characteristics, that is trends, oscillation, clustering, or mixture, then we can infer that the process is influenced by some assignable or special cause variation, and the process performance is also not stable. But then how to identify the non-randomness in a data distribution? We can apply these four rules to identify the same. If you find 6 consecutive data points showing an upward or downward trend, we would call that as non-randomness due to trends. Or if you observe 8 consecutive data points clustered on one side of the average line, then it would constitute non-randomness due to clustering. Or if you observe 14 consecutive data points alternating up and down the average line, so this would be non-randomness due to oscillation. Or if you find two sets of data points getting plotted at two different levels in a run chart, we would call that as non-randomness due to mixture. But then if you are constructing run chart using Minitab, so you'll be referring to this metric called p-value. So what is the criteria? So p-value greater than 0.05 for all the four non-random characteristics, we can infer that the data distribution is random. On the other hand, if p-value is less than 0.05 for any of the four non-random characteristics, then the data distribution will be considered as non-random due to that specific non-random characteristic. And then the final graphical format that we looked at was box whisker plot. So box whisker plot is the graphical tool which would help us to identify the presence of outlier or extreme value in a data set. So the box whisker plot will consist of a horizontal scale at the top with the data points flowing in an ascending order from left to right. That means the least value in the data set will be to the extreme left, and the maximum value in the data set will be to the extreme right. And down below this horizontal scale, we will construct the box whisker plot for this data set. So the box whisker plot will consist of a rectangle box at the center with two whiskers extending on either side of the rectangle box. So these whiskers are nothing but the horizontal lines extending from the rectangle box on either side. So the entire box whisker plot will be segregated in terms of quartiles. So the left-hand tip of the whisker will be Q0, which is the outlier limit on the lower side. The left-hand tip of the rectangle box will be Q1, which is the first quartile or the 25th percentile. So meaning, if you have 100 data points arranged in an ascending order, the value lying in the 25th position will be Q1. And Q2 is the center of the rectangle box. So this is called as second quartile or 50th percentile. That means if you have 100 data points arranged in an ascending order, the value lying in the 50th position will be Q2. And this is the central value in the data set, and hence Q2 will be referred as median. And then Q3 is the third quartile or the 75th percentile. Again, if you have 100 data points arranged in an ascending order, the value lying in the 75th position will be Q3. And finally, Q4 will be the right-hand tip of the whisker, and this is the outlier limit on the upper side of the data spectrum, right? So while Q1, Q2, and Q3 can be ascertained from the data set, Q0 and Q4 needs to be calculated by applying a manual formula. And for that, first we need to calculate IQR. So IQR is interquartile range, which is nothing but the length of the rectangle box and can be calculated by applying the formula Q3 minus Q1. So with this IQR value, we can calculate Q0 and Q4. So Q0 will be Q1 minus 1.5 into IQR. Q4 will be Q3 plus 1.5 into IQR. So once we have the Q0 and Q4 values, we can find out whether there is any data point in the data set which is either less than Q0 or greater than Q4, then that data point will be considered as outlier or extreme value. But then if you are constructing box whisker plot using Excel, then there is no need for us to perform all these calculations. We will be able to clearly find out if the data set contains any outlier value, because that outlier value will get represented by a dot in the box whisker plot constructed to Excel, right? So we also worked out some 3 exercises under descriptive statistics, and then we calculated not only the descriptive statistics measures, but we also perform the box whisker plot calculations in order to identify whether the data set contains any outlier value or not, right? And we also looked at how to calculate the Q4 value for a given data set using our template. And we also could understand that the box whisker plot, we will have 25% of the data points that would lie beyond Q3. Because in a box whisker plot, why these points are called as quartiles? Because the subsequent quartile points will be separated by a distance of 25% of the data points in the data set. So the first 25% of the data points in the data set will lie between Q0 and Q1. The next 25% between Q1 and Q2, the third 25% between Q2 and Q3, and the final 25% between Q3 and Q4. So the percentage of data points that would lie beyond Q3 is 25%. The final exercise, we also understood that if the average performance is pretty much similar, then we need to look at the consistency in the performance in order to evaluate a better performing category. And we also saw how to construct the box whisker plot side by side in order to make that comparison. So when a particular category has lesser variation, so that would be reflected in the length of the box whisker plot constructed for that category, right? So we will have the length of the box whisker plot on the shorter side for the category which has lesser variation. Fine. And then we moved on to the concept of yield. So concept of yield, we looked at how to calculate the roll throughput yield value. So for this, as I told you, you'll be provided with the throughput yield values, right, as a percentage values in the question, and you'll be asked to calculate the RTY value in percentage. So when we have the percentage throughput values given as input values, first and foremost, we need to convert all these percentage values in terms of decimals and simply multiply them to arrive at the roll throughput yield in decimal, and that decimal roll throughput yield value can be converted and expressed in terms of percentage. And then we looked at a very important chapter called measurement system analysis. So measurement system analysis is an exercise which would help us to validate the correctness of the base data that we have collated for the CTQ metric. And in fact, measurement system analysis is the first activity that we will perform as part of the measure phase. So measurement system analysis, as we could understand, is supposed to be performed on a routine basis, not just at the time of a Six Sigma project exercise. Because when we perform this exercise on a routine basis, we will not be exposed to any kind of surprises during the Six Sigma project exercise. But then if you are going to, if you are performing this exercise for the first time while working on a Six Sigma project, then in that case, you can also encounter a scenario wherein the measurement system may not be working fine, and you might have to discard the data provided by that measurement system, correct the measurement system, and collate the data all over once again, which would only result in delay completion of the Six Sigma project exercise. So when it comes to discrete data measurement system analysis, the quality inspectors alone will be part of the measurement system. But when it comes to continuous data measurement system analysis, we will have both the measuring equipment and also the appraiser using that measuring equipment being part of the measurement system. And then how to find out whether the measurement system is working fine or not, we need to look at the variation contributed by the measurement system. So whatever variation that we would observe in the output data set will be a combination of the variation contributed by the process as well as the variation contributed by the measurement system. But in a Six Sigma project, our effort or focus will be to reduce the process variation. And for that, we need to ensure that the measurement system variation is less than 10%. So only if it is less than 10%, we can infer that the measurement system is actually working fine, and we can proceed with the data provided by that measurement system for further analysis. But then if the measurement system variation is going to be greater than 10%, then we need to discard the data provided by that measurement system. Then discrete data measurement system analysis, the name of the exercise is also called as attribute gauge R&R agreement analysis. So attribute, as we could understand, is the other name for discrete, right? So attribute gauge R&R agreement analysis. So we will have some minimum of 30 samples to be considered for this exercise, and these 30 samples will be a proper mix of both defective and non-defective sample units. And we will have minimum of 2 quality inspectors involved in this exercise, and each quality inspector will be subjected to minimum of 2 trials. And once the quality inspectors perform these trials covering all the 30 samples independently 2 times, then we will have the results provided by them for all the 30 samples and also for both the trials. And apart from the auditor provided results, we will also have the SME result provided to us for all the 30 samples. And these subject matter expert results will be considered as the true value or the reference value. So in Minitab, right, if you are going to perform this exercise or if you are going to perform the calculations based on the output that we have collated post conducting the exercise, So we'll be referring to a metric called kappa value. So kappa value for all the measurement system variation matrices should be ideally greater than 0.9. If it is between 0.75 and 0.9, we need to marginally accept the data with necessary approvals provided by the leadership. But if the kappa value is going to be less than 0.75, then we need to discard the data provided by the measurement system, correct the measurement system, and collate the data all over once again. And what are the various matrices that we have which would define the variation contributed by the measurement system? The first one is repeatability. So what is repeatability? So this is the consistency of results provided by an auditor for multiple trials for a particular sample. So any mismatch in the trial results provided by an auditor would constitute repeatability variation. And then we have reproducibility, which is the consistency of the results provided by multiple auditors or inspectors for a particular sample. So any mismatch in the auditor or inspected provided results will be considered as reproducibility variation. And then we have accuracy, which is the consistency of auditor provided results when compared with the true value, which is the SME result. So any variation here would constitute accuracy variation. So all the above three matrices, the variation percentage or the mismatch percentage should be ideally less than 10%. Right? If it is exceeding 10%, then we need to discard the data provided by the measurement system. Or we can also look at the kappa value, which will be the metric provided by the Minitab. Right? And we also looked at how to perform the continuous data measurement system analysis. So for continuous data, it's enough if we have only 10 samples considered for the exercise, and we need to have minimum of 2 appraisers, and we need to have minimum of 2 measurement values for each sample unit provided by these 2 appraisers. And then we will calculate the measurement system variation matrices for a continuous data scenario. So the first one is bias, which is nothing but the differences in the average of the measurement values provided by the multiple appraisers and the reference value. So this reference value for a sample unit can be obtained by having the sample unit measured by the master equipment, which will be available in the central laboratory. So if you don't have access to that master equipment, then we'll not be able to calculate the bias metric. And then we have repeatability variation, which is also referred as gauge variation. So the repeatability variation is nothing but the differences observed in the measurement values provided by an appraiser when he or she measures the same part using the same gauge multiple times. And then we have reproducibility variation, which is also called as appraiser variation. And these are the differences in the average of the measurement values provided by multiple appraisers when they measure the same part using the same gauge. But then if the overall gauge R&R variation is in excess of 10%, and if you observe the repeatability variation to be significantly higher than the reproducibility variation, then we need to infer that the problem lies with the measuring equipment, and we need to provide this measuring equipment for necessary calibration. On the other hand, if you observe the reproducibility variation to be significantly higher than the repeatability variation, then we need to infer that the problem lies with the appraisers, and we need to identify those appraisers who are not handling the measuring equipment in a proper way, and we need to retrain them. So this is the corrective action that we will take when the reproducibility variation is significantly higher than the repeatability variation. And then we stepped into probability distribution. So probability is the chances of occurrence of an event, and distribution is the signature of a data set. So if you look at a particular data set, so that data set will follow a certain distribution. So for discrete data, we have binomial distribution and Poisson distribution. So binary discrete data would follow binomial distribution, and proportion is the primary metric. Whereas count discrete data would follow Poisson distribution, and average denoted by lambda is the primary metric. So under continuous data probability distribution, we have normal distribution. So normal distribution will be represented by a symmetric bell curve, which is the resultant output of a histogram. And the primary matrices for a normal distribution are mean and standard deviation. And then we also looked at the concept of standard normal distribution. For a standard normal distribution, we understood that the mean will always be equal to 0 and standard deviation will always be equal to 1. And then we looked at the area coverage within the various sigma limits for a normal distribution. So the area coverage within one sigma limit is 0.6827 or 68.27%, which means if the process adherence to customer specification is to the extent of 68.27% of the overall production, then the process is said to be functioning at just one sigma level, where the percentage non-conformance will be 31.73%. The area coverage within two sigma limits is 0.9545 or 95.45%, which would indicate that if the process per adherence to the customer specification is to the extent of 95.45%, process is performing at 2 sigma level. And area coverage within 3 sigma limits is 99.73%, which would indicate that if the process adherence to customer specification is to the extent of 99.73%, then the process is said to be functioning at 3 sigma level. And then we also looked at how to calculate the actual sigma level. And while calculating the actual sigma level, first and foremost, we need to look at whether the mean is aligning with the target or not for nominal the better kind of matrices. So for nominal the better kind of matrices, both LSL and USL will be provided to us, and target will be the midpoint between LSL and USL. So the mean is aligning with the target, and that is the position where mean can actually provide its best performance. We would call that process as centered process. But then if mean is aligning with the target, as we could understand, we can apply either the LSL side formula or the USL side formula to calculate the sigma level. So what is sigma level? Conceptually speaking, sigma level is nothing but the number of standard deviations we are able to pack between mean and USL or between mean and LSL, whichever is minimum. So if the mean is aligning with the target, the minimum doesn't arise at all, right? And then we could also understand that the standard deviation and sigma level are contradicting matrices because standard deviation is in the denominator in the sigma level formula. So reduction in standard deviation would help us to improve the sigma level and vice versa. And we also understood the relationship between the long-term and short-term sigma levels as per Motorola. So long-term sigma level will always be 1.5 less than the short-term sigma level. And today we looked at how to perform the normality test. And for performing the normality test in Minitab, so we will be applying Anderson-Darling test and be looking at the p-value. So p-value greater than 0.05, so we can infer that the data distribution is normal. On the other hand, if p-value is going to be less than 0.05, we need to infer that the data distribution is non-normal. And we also looked at how to convert a non-normal data set into a normal data set. So we need to adopt a stepwise approach. As the first step, we need to obtain the square root values of the original data points and then validate these square root values data set for normality. So if the square root values data set fails in the normality test, then we need to obtain natural logarithmic values for the original data set. And we need to test the natural logarithmic values for normality. If the natural logarithmic values data set also fails in the normality test, then as a final step, we need to perform a transformation called box-box transformation. But then as I told you, we need to be aware of the fact that while performing the conversion, there could be a potential loss of information with regard to the original data characteristic. And then as a final chapter in the measure phase, we looked at the process capability analysis. So process capability is the ability of the process to meet the customer requirements. So we have the process capability analysis applicable for both discrete as well as for continuous data scenarios. So discrete process capability analysis, we understood the difference between defect and a defective. So defect is nothing but the error identified at an inspection parameter or an audit parameter level, whereas defective will always be referred from a unit perspective. A defective unit can contain one or multiple defects in it. And we also understood the terminology called opportunities for error. So these are nothing but the number of inspection parameters that we would consider for quality inspection. And the number of OFEs would signify the complexity of the process. So higher the number of OFEs, we can understand that the process is very, very complex and vice versa. So we will be able to compare the defect rate of two entirely different set of operations when we consider the opportunities for error in my calculation. And we looked at the various process capability matrices applicable both for defects as well as for defectives data. So for defects, we have DPU, which is defects per unit, and DPO, which is defects per opportunity. And from this DPO value, we can extrapolate and arrive at DPMO, which is defects per million opportunity. And finally, we will be able to calculate the sigma level by considering the DPO value, right? So when we calculate the same set of matrices from a defective perspective, the calculation will be slightly stricter. So when it comes to defectives, the defectives per unit and defectives per opportunity will be one and the same, because the number of opportunities that we would consider when we calculate from a defectives perspective will always be one. Because when we look at it from a sample unit perspective, the sample unit can either be defective or non-defective. So the opportunity of that sample unit being defective will always be one, irrespective of the complexity of the process. And this is where the defectives calculation will become or would become much more stricter than the defects calculation. Because in the case of defects calculation, we have the cushion of considering the total number of opportunities while calculating the defect, right? That's the key difference. And we also worked out some 3 exercises under discrete process capability analysis. And then we moved on to the final section, the measured phase, which is the continuous process capability analysis. And this process capability analysis is applicable for a normal distribution. So we again have 3 matrices here, CP, CPK, and sigma level. So CP is referred as the potential capability, CPK is the achieved capability, and from this CPK value, we can also calculate the sigma level. So this sigma level calculation is pretty much similar to the sigma level calculation that we saw under normal distribution. The only difference is we are calculating this sigma level from the CPK value. So CP, as we could see, will always be greater than or equal to CPK. So CP, the potential capability, can be derived by using the formula USL minus LSL divided by 6 times the standard deviation. So USL minus LSL would indicate the customer tolerance, and 6 times the standard deviation would indicate the process variation. But then if the customer tolerance is greater than the process variation, then the resultant CP value will be greater than 1, which would indicate that the process is capable by design to meet the customer requirements. But if the customer tolerance is less than the process variation, then the resultant CP value will be less than 1, which would indicate that the process is not capable by design to meet the customer requirements. So what is the problem with CP? So CP as a metric would only indicate the potential capability of the process. But if you want to understand the current performance or the achieved capability of the process, we need to consider CPK and sigma level. But then CP in its formula doesn't even consider positioning of mean. So that is why CP will not be able to provide information with regard to the current performance or the achieved capability of the process. So while calculating CPK, so we would be applying a formula which will be similar to our sigma level formula. So the only difference is the denominator will have 3 times the standard deviation, whereas when we calculate the sigma level, we will have only the standard deviation in the denominator. So hence, the sigma level will be 3 times the CPK. So sigma level and CPK are closely connected with each other. So sigma level will be 3 times the CPK. So we looked at some 3 process scenarios and we could draw some inferences out of it. The first process scenario, so when mean is aligning with the target, so we will have the CPK measure performing up to the CP level. So we have said that CP will always be greater than or equal to CPK. So when CP will be equal to CPK, when mean is aligning with the target. When mean is aligning with one of the specification limit, then both CPK and sigma level will be equal to 0. So this is a scenario wherein we will have only 50% process adherence to the customer specification. So when we have 68.27%, the sigma level will be equal to 1. But when we have only 50% process adherence to customer specification, the sigma level will be equal to 0. And when the mean is positioned outside the specification limits, both sigma level and CPK will be in negative. So we will have a scenario where there will be less than 50% adherence to the customer specification. So we will be able to improve CPK performance up to CP level by aligning mean with the target, which is the first objective of Six Sigma. But then if you want to improve CP as such, then we need to look at reducing the variation, which is the second objective of Six Sigma. Right? So at the end of the measure phase, we will not only have the baseline performance of the CTQ metric, but we would have also calculated the baseline sigma level. And in the third phase, which is the analyze phase, we would be focusing on identifying the causes and the root causes for the business problem. So as I told you, during the define and measure phase, our complete focus would have been on identifying and defining the business problem and also measuring the CTQ metric performance, which would help us to quantify that business problem and expressing the CTQ metric performance in terms of sigma level, which would be the baseline sigma level. But only in the analyze phase, we would be shifting our focus towards identification of causes or root causes for the business problem. So in that transformation equation that we saw as part of the introduction phase, y is equal to f of x plus epsilon. So y as an effect, right? So we will be completely focusing on this y during the define and measure phase. Only in the analyze phase, we would be shifting our focus towards identification of excess, right? And there are certain deliverables which we need to adhere as part of the analyze phase. So the analyze phase, we will start by brainstorming for probable causes, and then we will categorize all these probable causes in a pictorial format called cause and effect diagram. And then we will perform 5Y analysis, which is also called as root cause analysis, in order to identify the root cause for a given high level cause. This is very, very important. And then we will prioritize identifying the vital few causes, right, through some prioritization tools like Pareto analysis, control impact matrix, and subjective multi-voting. And we would validate the significance of these vital few causes with respect to the business problem by performing a statistical exercise called testing of hypothesis. And then we would establish the relationship between the business problem and the vital cause by constructing a scatter plot and also objectively measuring the strength of that relationship by performing correlation analysis. And then finally, the analyze phase, we will build a regression model, the format y is equal to f of x plus epsilon. So we look at the details of all these deliverables tomorrow. So we will close our session here for the day, and we will continue with our discussions with regard to the deliverables under analyze phase tomorrow, right? So have a good night. We will connect at the same time tomorrow evening. Thanks for your time.
Thank you.
Thank you, Sridhar.
Thank you.
Thank
Bye-bye.
you.
Thank you.